Welcome to another video, I guess, where I develop Plum in the programming language. This time I want to look at reference counting. I implemented reference counting before in another video. I can link that somewhere here. But I kind of removed reference counting when migrating from a backend that compiles to C to a backend that compiles to a custom bytecode. Just because there was a lot of other complexity going on at the time. I had to decide on memory layouts, on converting the code into a stack-based machine. Like that, there was a lot of other complexity that got shoved into this low-level stage. So I just thought, hey, reference counting is not essential right now for the semantics, so I'm gonna leave that out. And I think that was the right decision, because that allowed me to kind of iterate on that and kind of chew on these lower level details until some nice abstractions emerged. And that's kind of what happened. So I'm happy with how the backend is architected right now. I'm gonna give you a quick tour of that, hang on. Maybe this one, yes. So here we have the compiler stages, or the compiler stages. And the yogurt is your official graph using resolved types. So this is a representation of the program where all types are known to the compiler, where you have these simple expressions. Let's maybe look at that. Yeah, these simple operations like create a struct, or access the member of a struct, or switch on some value. And these all reference each other using IDs. And these operations, each of these operations is in a body, or like in a function, as expressions, which associates the operation with the type of the result. Right. So at this stage, having something like reference counting doesn't really make sense, because we don't know memory layouts yet. For example, if you have some sort of struct, maybe a player struct with a position and some health data, maybe that, yeah. Then in memory, this will be, the position has an X and Y coordinate, and the health may be an integer. But in memory, all of these are next to each other. So it's not like there are pointers for every field that point to other objects in memory somewhere, but we try to inline most of these structs, because that's more efficient than storing pointers everywhere. We do store pointers, however, for recursive enums, like linked lists or something, because for recursive enums we don't know the final size. They can be infinitely large. And that's actually the only place where we store pointer interactions. Yeah, and that happens in the waffle, the compiler stage after the yogurt. The waffle is a well-aligned form of fixed layout expressions. So it's kind of similar to the yogurt in that you have these expressions in your code, and every expression is something like a call, like a switch. But these don't operate on types anymore. Instead, they have there's, for example, this aggregate expression, which takes some other expressions and puts them in memory next to each other. Every expression is just some memory with a size and an alignment and this kind. And that makes things a little bit easier for the next, for compiling this waffle to bytecode. Because here we don't need to care about types anymore. Types basically don't exist. Instead, for example, if you have our player again with health and position, if you access the position, that may just be like a waffle member of this player expression, whatever that may be. And we just say, well, offset the memory at, get the memory at offset 8, for example, for the position of some size 16 maybe. And then position dot x and y, again, they are just waffle members with different offsets. So there are no fields with names anymore. There are no types. There's no, like, everything is kind of this homogeneous byte level, memory level representation. And the waffle, contrary to the yogurt, also allows nesting of expressions. In the yogurt, these expressions reference each other only via IDs. For example, to create a struct, you have these mapped from field names to IDs. And ID is basically an index into this list of expressions that a function owns. And all of these, they just have yogurt IDs as, you know, for referencing other expressions, rather than storing the expressions directly here as a real tree. And that makes sense because you may have, you may store some variable or something, and then you may do multiple calls that depend on that same variable. And you don't want to compute that variable twice. And actually it's not, if calls do something like peg, well, you could maybe call that twice. Anyways, the point being, everything is this flat hierarchy of operations rather than a nesting of expressions. In the waffle, however, we do allow nesting. For example, here we have a waffle expression padding and a waffle expression, I don't know, int value or something. This has a size of 8 bytes, this is 1 byte, and we put them in an aggregate. And this again is in a switch of some other more complicated expression and so on. So the waffle has this tree structure because when converting the waffle to bytecode, that is very useful. The bytecode is stack-based, so we can just walk the tree from inside out and put elements on the stack. Yeah, for example, to create this aggregate, maybe I can show that. Yeah, we just compile each of these fields. Because everything is stack-based, creating a point with x and y, for example, is similar to just compiling the expression that results in x, whether that's like a complicated call or something, and then compiling y, the code required for computing y. And you don't need to do anything more. You don't need to create a struct or something, because just putting these two things on the stack is already like putting the struct on the stack. Yeah. And the question is, how do I integrate reference counting into that? The solution, I believe, is to create a new compiler stage. Because in the waffle, in the yogurt, it doesn't really fit. The yogurt doesn't have memory layouts, and we basically want to keep a reference count for each heap allocation. That kind of tracks how many references are there to this allocation, so that we can then free the memory when it's no longer referenced by the code. Yeah, I have, yeah, so it's not going to go in the yogurt, this reference counting stuff. But I think the waffle is actually also pretty low level for that, kind of. Because in the waffle, we have things like, where's that? Something like load and store, I think. Hang on, we do stuff. Oh, we don't have any sort of free. Hang on, how do we? Oh yeah, the waffle is completely immutable, I think. You can only reference an existing parameter, create some padding, create a byte, create a word, reference some other local ID, create an aggregate, create a member, but you can never mutate data, I think. Hang on, switch, call indirect. There's a function pointer, sure. These all consume, well, they kind of combine existing waffle expressions to one waffle expression. But yeah, all of this is just basically an immutable description of how data flows through your program. There is no mutation of now increase this reference count or something. Yeah, and I want to keep it that way, by the way. I don't want to, well, maybe it makes sense actually to kind of have extra reference counting operations in here. Yeah. Probably makes sense. Yeah, in this example, there is no reference counting, but for example, if you iterate over a linked list, or like you map a linked list or something, each function should take kind of an ownership of the parameter. Let's maybe write that down. So here there is a list type defined as a struct, an end type, containing, hang on, let me maybe increase the font size a bit. Yeah. Containing an item, list of t, yeah, an item and the next list item. Oh, hang on, a list can also be empty. So there's actually an enum type with either empty or more, containing a struct of the item and the rest of the list, which will be another list of t. Yeah. The way we memory layout these is that, hang on, let me play that through. This is an enum, so it has the payload and then a single tag that tells whether this is empty or more. If this is empty, then this right here is just garbage, and the tag is 0. They are sorted alphabetically, empty and more. Yeah. If this is a 1, then this represents this struct. And that depends on the t. Let's say we have a list of int. How is this memory layouted? Memory layout of list int. It's either some garbage and 0, also 1, and then this contains the struct, which will be a t, so an int. I'm going to put an I in here, I think, for int. And an int is always 8 bytes, so 1, 2, 3, 4, 1, 2, 3, 4, and then the rest, which is again a list t, and this is recursive, so this is a pointer. I'm going to put 8 bytes here as well, 1, 2, 3, 4, 5, 6, 7, 8, yeah. And this means that this has the same size. Yeah, the memory layout will be something like this. In the empty case, just 16 bytes of garbage and then a 0. In the more tag, just have the integer right there, and then a pointer to the next list item and a 1. Now the question is, what if you have a map function that takes a list t, like let's say an increment function, that takes a list of int and returns a list of int. And what it does is it returns a list where each item is the item plus 1, basically. So I think what it should do is switch on the list. If it's empty, then it's just going to return an empty list. If it's more with an item and the rest, then it's going to return more with your item being the item plus 1 and the rest being increment of rest, calling ourselves recursively. Yeah, the way that should look in, what I could actually, let's maybe put this into the file and see what happens, and then see how reference counting could be applied to that. Hang on, there's the workspace and the core library. There's also a test playground. Yeah, so now we have this increment function, and this list we're just going to increment that, and then return 0, I don't know. Yeah. Okay, yeah, let's compile that and see what happens. Expected expression after parentheses. Ooh, okay. Well, this is, yeah. Again, this language is not finished. I think for now structs they have to be multi-line. You can't have these on the same line. So it has to look like this, which is more readable, I guess, but still. I think then we can even remove these. If it's empty, then empty. If it's more, then more of the item and the rest. Okay, so this doesn't match. It claims that it returns this right here, which it should. Oh, I see. More doesn't. Your list is defined in the standard library, not as more of a struct with the rest and with the item at the rest, but just as more with these directly as enum payloads. Which means these are kind of more like this. More of an item and the rest incremented. Nice. Assembling. Welcome. Result 0. Okay, that seems correct. But let's look at the waffle. So in here, in the compilation pipeline, hang on, compile, waffle is this to waffle. Let's print that waffle. Okay, so we have a main function that is fine. Oh, it's all constant folded to, because the list is known at compile time. It just creates the numbers, sure, then does some other stuff, creates the numbers again, I guess. And then it just creates these linked list nodes. Like this is a linked list. Hang on, this is a linked list of in here is sorry, 0, 1, whatever that means. Oh, this is a linked list of 1, 2, and 3. And these are the tags. Empty, more, and more. The tags being 1 byte. And these are the integers 1, 2, 3. And there's another list of 1, 2, 3. And here's the mapped list of 2, 3, 4. Which is, yeah. Generally, we want to optimize that code. But in this case, we actually want to see the waffle for that increment function. So this list cannot be compile time known. So let's maybe do like a create make list, I don't know, with a length, which will be an integer, and then what this will do is, well, it's gonna check if the integer is 0. I think this is not supported. I think there's compare, there is, I should have some, well, there was less and there was greater. What more do you want, right? Oh, I think you can't have equal signs in function names right now. I want to add that, but So let's maybe have some equal function, taking an a and a b, producing a bool. It's just going to compare a and b. If it's less, it's going to return false. If it's equal, it's going to return true. If it's greater, it's going to return false. So here we can check, is length equal to 0? Oh, I think there's an is empty on list. Maybe not. Oh yeah, there is. Well, that makes things a bit cleaner. I know, we don't have a list, we just have the length. Okay, so if the length is 0, then it's just going to be empty. Otherwise, this is a list of that length, like of, let's say 42, I don't know, 42, and make list of len minus 1. Okay, and this returns a list of ints. And then in here we can just say make list of this runtime known argument to the main function, which is always 5, I think, but yeah. This is, like, the compiler is not finished. The compiler is definitely a prototype. And things are hard-coded and so on, but I just want to get the language working instead of working on the finishing touches. There is no function named equal. Oh, that makes sense, because int has to export equal. Oh, there is equals. Right. There is equals. Well, that is... Okay, I guess I'm going to put that a bit more up here, because it's a bit more fundamental. And remove this, and then just use equals in here. Well, there is no function named equals. Oh, because we have to import that, probably. Modules and imports doing their thing. There is no. You have to import minus. Well, you do what you gotta do. Oh, and len probably as well. Probably. Oh, now this worked. Well, okay. Okay, so what do? We have, oh, we have a lot more functions now. We have compare ints, add ints, sub ints. We have the plus function. We have the equals function. We have casting stuff. Hang on, there's the same type, but I mean, sure, you can cast that, I guess. Oh yeah, and it just returns the argument. Sure. And we have minus, we have more casting int, we have make list. Sure. Sure. Cast, built-in main, built-in inc. This is the interesting part. This is the part I want to look at. Okay. That's quite a lot of code. Okay, it takes the argument, the part from 0 to 17, aka the entire argument, and then at offset 16 there is the single byte representing the enum tag. If that's a 0, then this is an empty, the empty variant. In that case, we just return an empty list, which will be 25 bytes of padding followed by 1 byte of 0 indicating empty. I'm not sure why 25 bytes, but who am I to judge, right? Okay. And if there is more, oh yeah, if the thingy here is not 0, then then we do this. We take, hang on, we cast int to int, sure. We have a 1 and another 1. Yeah, we add our int and 1 to get the incremented, to get an incremented integer. This is a no-op, I think, because this, yeah, this doesn't do anything, but it does unbox something, so it gets something from the heap, from the argument at offset 8. I think that's the pointer to the next list item, length 8. It unboxes that, aka dereferences that pointer to the next list item 17 bytes in memory, and it gets that as an expression. Sure, and then it calls itself recursively using that next list item. And finally, it's in here it puts our incremented integer, the mapped rest of the list, and then this 0, because this is always, the type of this is this, and enum, there's always more. So yeah, 0 is the tag for more in that case, because there is only one tag. But then it casts that to an enum of empty or more. So this 0 will then become a 1. And that's what's returned. And then here we cast things again. But these are the same type, I think. Oh yeah, they're kind of the same. Yeah. Okay. So how does that work? I think where would we have, let me maybe copy this and then insert, like manually insert reference counting operations and see where, like how they would flow through that in the waffle, I guess. Yeah, so this is the generated waffle for that function. And what we do here is, if a function is, if we have a list with reference count 1 and we want to increment that, we should create a new list, but we should also free the old list. So what we need to do, I think, is in here, if this is an empty list, this case is actually correct. We just create an empty list and return that. There is no thing on the heap allocated. But for this case, we need to do something. Let's see. We know that we have this this variable that contains a pointer. So what we do is we we cast stuff, sure, we increment integers, fine. Yeah. Here we unbox that pointer, which is fine. We increment that, we create a new list item. Sure. Yeah. And in here, right before we kind of evaluate to that, I think in here we also want to kind of drop this list, drop this variable. Ooh. So basically, we take by being passed this value as an argument, we kind of take ownership of that. At least we take responsibility for one reference count of that. So at the end of our scope, we need to decrement the reference count by 1. Yeah, that's the correct approach. And then, yeah, later on we can optimize that and do more crazy stuff. But for now, I think that's a sane approach. Just whenever you create stuff on the heap, aka with this box kind of thing, you want to increment, whenever you create something on the heap, you want to increment the you want it to have a reference count of 1, and whenever you copy something, for example, if you put something into a local variable, you want to increment that the reference count of that heap allocated thing. And when a variable goes out of scope, you want to drop that variable. And if it contains any pointers, then you want to kind of like dropping an int, for example, does nothing. But dropping something that may potentially contain pointers, like a list, means that you have to switch on the list and see is it the which variant is it, and if it is something that contains pointers, then I'll decrement the reference count of those heap objects. Okay, the question is, do I want to put that into the waffle, or do I want to add a compiler stage below that? I'm actually not entirely sure. Let's see if there's like a semantic, if this is like semantically sane enough to think about. So in this compiler stage, yeah, it's tree based. Maybe that should be a separate stage, I don't know. But the important part is that each expression corresponds to a slice of bytes. And yeah, now we want to implement incrementing and decrementing reference counts of these expressions, I think. Yeah, and I think like the duplication and like the reference count operations, they should be in this compiler stage as well, because we can't add them once we have this stage. If we're just looking at, oh, this variable goes out of scope, we know nothing about this. We don't know which type it came from. We only know that it is like 8 bytes or something. That tells us nothing. Like here, oh, this goes out of scope. This 26 byte value. We don't know which of these bytes may represent a pointer. We don't know if it's an enum. We don't. This reference count handling is type specific. So it needs to happen during this conversion from yogurt to waffle. Yeah, which begs the question, like irrespective of how we continue from the waffle, I may add a compiler stage after the waffle that takes care of this, turning that into more of a tree-based thing, and then also special, or like removing the reference counting operations, kind of, turning these into memory reads and writes. I don't know. But the important part is that in this compiler stage, I think the semantics should be reference counting should be a first class thing in here. You can create aggregates in here. You can access stuff, but there should also be a where are the heap things here. You can box something, aka create a new object on the heap of some waffle expression. You can unbox something. And I think you should also be able to dupe something, aka increase the reference count by 1 of some pointer, and drop something which will decrement the reference count by 1. And free that thing if the reference count reaches 0, for which it needs the side. No, actually not. Yeah, but something like this. You also have dupe and drop as first class operations. So I imagine what would happen is in here we could put something like a call maybe to some drop function. Oh yeah, we could create, I think that's what we did for the C backend, create a function for duping and dropping every type. For every type that occurs in our program, we create such a function. So we could have, just call a function. What kind of things do we have in scope? We have this, we have 11 here. Okay, I think I'm going to not make this as tree-based as it currently is. No, well, okay, I think this is actually fine. This is an enum or something, I think. Yeah, and then right here, before the scope ends, we want to drop that. What did we create here? We created an empty enum. So here we want to call, drop enum of empty with 1, and this will decrement the reference count of this type. Yeah, and yeah, in reality though, because this is a value, nothing needs to happen there. Like drop of empty does nothing. And similarly in here, we would do, let's see, call drop of int, I guess, of 3. We would do drop of int of 4, drop of int of 5, drop of int of 6, drop of this right here. Of 7. We would do increment of drop of that temporary result. Okay, what is 9? 9 is this right here. is this. Amazing. Amazing. Okay, so all of these get dropped. But when creating, no, hang on, when referencing these values in other expressions, we increment the reference count. So this right here calls cast int to int with 0 thingy, this right here, which is this kind of list. So what we do here is we call dupe of that list of, you know, this, I think, or this list. No, this thing. Oh, and this is just an integer. Well, so dupe of an integer does nothing. But because that integer is used in here, we dupe that. And this uses 4 and 5. So before we dupe 4 and 5. Makes sense. This right here references unbox things, and yeah, this is an argument, so we need to increment the reference count of that. Actually, I see that these dupe and drop implementations, they are type specific. And they don't really, you know, they don't depend on the data structure, I guess, on the type. Like what we could do is in the yogurt or something between the yogurt and waffle, introduce a compiler stage there that has dupe as this thing, not just a call, but as a real expression or something. Whenever we use an expression in another expression, in a call or something, we dupe that beforehand. And when things go out of scope, we drop them. And then when converting that to the waffle, this is where we can kind of specialize that dupe and drop behavior per type. But in the stage before, we could even kind of see where this behavior cancels out, maybe. This is weird. This is weird. Because I see that duping and dropping something is like when you want to specialize that depends on the concrete type, but the concept itself is not type specific. let me maybe pull up a paper. So there is this, I don't even know how it's called, Perseus, yeah, garbage-free reference counting paper, which talks about how you can optimize these dupe and drop operations. And they have something that is specific to types. So here they do this basically. Many compilers emit code similar to this. At the end of the scope, you just drop these values. Let me maybe zoom in a bit more. Yeah. And there is also the dupe operation, which increments the reference count. And what they do is they say that a function taking a function taking an argument kind of takes ownership of that value. I don't know where they say that, but yeah. Ownership of references is passed down into each function. If you pass something to a function like this, like the map function, that map function is in charge of freeing the arguments. So within the surrounding function, you don't need to have these, and that makes a lot of sense, I think, because then you can drop these values as early as possible. And what they see here is that for many operations, like for example list mapping operations, pushing this reference counting down actually means that it can maybe be unified with creating values. So if you have a list map function, down in the mapping function somewhere new list items are being created. So it makes no sense to keep around this entire list function at the top scope, in the outer function scope, then map this entire list to another list, and then free the original list. But what they do is they push ownership into this map function, and then the map function, because it interleaves this freeing of old list nodes and allocating of new list nodes, you can reuse the memory directly. So basically, mapping happens as it actually mutates the list in memory. That's what happens naturally as a result of that. Yeah. And kind of reuse that memory. Yeah. And I'm not going to do something as complicated as this in the beginning, but it would be nice to have the option for that. And I think the semantics of if you call a function, you kind of give ownership of that value to the function. That makes sense. Yeah. Yeah, there's just a lot of stuff. And specializing stuff based on reference counts and so on. Not really what I'm looking for right now, but it is really, really cool, and I may get around to do something like that eventually. So I think we need some, in the waffle, we need some sort of semantics for waffle expressions. Waffle expressions are memory regions, basically. But do objects have to be treated separately, or like a thing is on the heap? Currently there's just box and unbox, and I think it would make sense to I'm not sure. what makes me kind of hesitant is that having type-specific dupe and drop functions, in many cases, inlining these functions will be useful, especially inlining empty functions, aka just removing the function call. So I need some sort of function inlining in the waffle, which is fair, I think. Oh man. Yeah, let's add a compiler stage before the waffle that just inserts reference counting operations, and then we can see how that works out. Yeah, and we can just ignore those, by the way, when we convert that stage to the waffle, and the compiler pipeline will still work. And then we can figure out like which semantics do we want in the waffle, then compile those reference counting operations to the corresponding waffle stuff. Yeah, that seems reasonable. So I need a name for the new compiler stage. Well, it will be, the interesting part will be reference counting. Or like dupe and drop things. Oh, maybe pudding or something. Is that an English word? Pudding, I think so. With like D and D standing for dupe and drop. Yeah. The question is, what does that stand for? Yeah, I'm gonna figure that out. Okay, I have a name, pudding. Program. This is a representation of the program using dupe drop to immediately nuke garbage. That's amazing. I like that. So we have the waffle. Yeah, it's gonna be similar to the waffle, to the yogurt, I think. Yeah. Although I should maybe look at what kind of abstraction level is this? Do they have types in here? They don't really. That's kind of crazy. Okay, yeah, I see. So these are not really type specific here, these dupe and drop operations. They just, we want to dupe some value, want to drop some value, but it's not yet specialized to types. So I think it makes sense to do this before deciding on memory layouts and type specific stuff. Yeah, okay, so sure enough. Okay. It is weird that these compiler stages are so similar. I don't know what else to do. The thing is, these kind of right now the waffle has no side effects. Okay, there is the crash instruction somewhere, yeah, sure. But apart from that, you can reorder expressions. You can, do all crazy stuff. Yeah, I don't know. Okay, I'm gonna call this pudding. I'm just gonna create that, and let me just rename the padding, not padding, pudding signature, which will map to the pudding fun, which will map to pudding expression, pudding body ID. Okay. Yeah, so the thing is, dupe and drop, they are not expressions at all. They are statements, I guess. They don't have a result. You shouldn't even be able to refer to a dupe or drop operation. Which makes this a bit weird. Like, I don't want to have both expressions and statements, I think. Because in the next compiler stage, in the waffle, I'm wondering, all of this is expression based, and the idea is to treeify these expressions as much as possible. And to do that, the dupe and drop operations, they may get in the way. That's what I'm concerned about. Let's look at the complexity of this yogurt 2 waffle thing. Okay, this is manageable. This is really manageable. Like, this is not a lot of code. Okay, yeah, 300 lines. I think it would be possible to kind of add add dupe and drop things in here, maybe. I mean, the waffle has to be optimized later on. Anyways, so maybe this is not a big deal. Needing to drop every expression that is in scope. difficult. Okay, let's adjust this compiler stage without, let's, the padding, I'm gonna leave that there, not use that right now, maybe later, but I'm going to try to add reference counting stuff when converting the yogurt to the waffle. For these values, nothing needs to happen, I think. Yeah, these all have like a reference count of 1, basically. Yeah, and enums, like variants, they will just use waffle box to create a new object on the heap. That is very fair. Then to convert an expression to waffle is similarly simple. Yeah, but if we have an expression that references others, like this one, the waffle aggregate, yeah, we kind of need to also emit code for duping those other expressions, for incrementing their reference count. I took a long walk yesterday, and I kind of have a clear picture now what I want the pudding to be. So the main thing that changes among these different compiler stages is what information we get in the first part. From the bacon to toast to egg to yogurt, we gain ever more information. We first just get the annotation of the file, then we parse the content, then we turn this into a graph, then we resolve types. And then in the yogurt, we know everything there is to know about the program. We know what is the type of every expression, which functions are called. Like, we know how everything is connected. We have all the semantic information. And from the yogurt, we then try to boil that down into something that is more easy to understand, like that the computer can understand. We try to turn, for data types, we decide on memory layouts. We decide in which order we want to execute operations, how to lay out data structures in memory. We choose stack code, like stack bytecode instructions, stuff like that. And in the second part, I think there is some, the main difference between these representations is how do we store data? Okay, the data structures, the values that you pass around. In the yogurt, this is like a pure semantic level that we operate on. We just have these yogurt values, which is an enum that says, well, this is an int or string or struct or something. And we store the type, which is, again, purely semantic information. Like, this is a primitive type, this is a never type, this is a struct containing these other types. In the waffle, the next stage down, we no longer have that. In here, every expression is just some bytes in memory with a size and alignment and so on. And that's a pretty huge jump from we have these abstract data structures, these values, these types, and they just immediately get converted into bytes and concrete memory layouts. I think there is room in between for an extra step. Something like how we previously represented values in C. Back when Plum compiled to C code, we had this nice, we generated C code and actually like C structs. And they were more explicit than these waffle types because we decide where do we insert pointers, where do we insert reference counts, where do we, all this extra information. We did all of that without immediately thinking about, well, how do we lay out these fields in memory. That was what the C compiler did for us. And compiling to C was surprisingly easy. So I think the way to go is to model values similar to how we read, to how C data structures are stored. And this will be similar to these right here, to plum types, except these will be pudding types. And there will be no recursive types, I think. Not entirely sure about that one. Well, and instead we'll have pointers in here, like this. So, or like this, probably rather like this. Yeah, but the idea is that rather than just representing the semantic meaning of types, we make the decision when do we use indirection and when do we store values directly in line. We make that right here. And then converting that to memory access stuff later on. And what this allows us to do is that now we have a separation between values that live in heap memory somewhere, values where we have a pointer to that value, and values that are passed around by value. Right. Badly termed, I guess, but that are passed around by copying the actual bits. When do we pass around pointers? When do we copy the values? We have once we have a distinction between those two ways of transferring data, we can also insert kind of like dupe and drop instructions to say, well, that now this memory region here is referenced by another variable, so the reference count needs to be increased. And now that variable goes out of scope, so we decrease the reference count. And now these, this value is no longer referenced. We're going to free that. Stuff like this can be explicit in this intermediate representation, because we decide which values are stored between pointers somewhere in memory and which are not. And yeah, this means that we kind of can introduce that and think about that in isolation without also immediately having to think about the concrete memory layouts and how, like, where in memory are these bytes. If we have a struct of a position, I don't know, with x and y coordinate, we don't have to immediately think about at which offset do we store the x, at which offset do we store the y. This is more abstract than that. It's somewhere in between the yogurt representation and the waffle representation. And this pudding stage basically represents your program using dupe and drop instructions to neutralize, nuke, garbage. Yeah. Yeah, let's go with neutralize. Yeah, so this adds all the semantic stuff needed for reference counting and garbage collection before deciding on concrete memory layouts, which is, separating these twos and having these, tackling these, both of these are complex problems, and tackling these in isolation is more doable than doing everything at once. So the pudding will look similar to the yogurt, I think, except a little bit different, of course. Yeah, so let's see. I'm gonna just rename all yogurt to pudding here, and we'll see how that goes. So we have a pudding. That makes sense, I think. That maps pudding signatures to pudding functions. And these have expressions. Ooh, do they capture stuff? We can even, potentially, do this sort of lambda handling in here. Here we have, a lambda type. Should be pudding lambda type, I think. With the arguments and the return type. Maybe instead we could have something like a function pointer. That is a bit, lower level than lambdas, because lambdas also can capture variables and data from the outer scope. In here we could put that data in a struct or something explicit. So the closure of the lambda, we can desugar that into already in here, so we don't have to do that and deal with that later on. I think that makes sense. Okay, so yeah, the pudding is, what, let's put that actually below the type stuff. I'm not sure about the recursive type, how recursive types are represented in here. I mean, you could just say that pointer shouldn't grow infinitely. Well, I don't know what to do about that. Yeah, I'm just gonna have untyped pointers, maybe. I don't know if that is smart. We'll see. Okay, so we have the pudding function, pudding ID, which is an index into this expressions thingy. The individual bodies, they can have parameters, they can have expressions, they can return something. The pudding functions, they have expressions. And the body. Shouldn't they also accept arguments or something? Pretty sure they should. I'm not sure what to do about this captured thing for now. We're gonna get to that. Okay, pudding values. I think I'm going to remove these and instead, well, I don't know what to do, to be honest. Maybe I'll keep them right now. And
We'll see where this gets us. Now this is still plum type, yeah. Putting variant value. First a string. Right. We import the main file. We Okay, and the individual operations, they can be referencing a parameter, initializing and uninitializing values, having a comp time value in here. Again, I'm not entirely sure about these values and how comp time values are represented. I may just change that. Let's see, in the yogurt to waffle, what do we do about values? I think there's a separate to waffle of a value, yeah, where we just switch on these and turn them into kind of like aggregates or something. I don't know. Well. Yeah, I think it may actually make sense to not have a comp time stuff in here as a separate thing, but just say, you know, put these in there as well. Yeah, because there should be no difference, you know, from this compiler stage on between creating a struct with, you know, that is compile time known with known yogurt known pudding values, and creating a struct where one value is compile time known maybe and the other is not. When lowering this to the waffle, they will both be treated the same. This will both be in a waffle aggregate with, you know, one comp time thing and, well, a waffle call or a waffle value or whatever. So I think it makes sense to unify these. Not have a separate concept of comp time values in the pudding, because we do all of that in the yogurt and the special handling of comp time stuff and so on. Yeah. And here, instead of this, we just have these values directly. We can say this is an int, we have a string, we have a struct, like we do down here with putting IDs. We have variants. Oh, look at that. Yeah. And we have lambdas. Amazing. Okay. And then we also have like dupe of some value of some pudding ID and drop, which increments and decrements the reference count of expressions. Amazing. Okay, so thinking maybe dupe and drop are like separate concepts or something. Again, we'll leave them in here and maybe later on I'll refactor that. The important part is just getting started and having something and yeah, making that perfect and so on. We can always do that later. Yeah, let's put that up here after all. And yeah, putting types where they're used actually in here. returns pudding ID. These have a pudding type. Okay, let's actually put that down then. I'm pudding op and pudding type. Here are the ops. Here are the types. Amazing. And then instead of yogurt to waffle, we do yogurt to pudding. Okay, yeah. Yeah, I'm not gonna, like, values are like a separate topic, I guess. Let's first look at expressions, because I think it's more straightforward to lower these. Or maybe start even further down. To pudding of a yogurt body should result in a pudding body. I agree, that makes sense. And here we have a fun builder, yogurt ID to pudding expression. Now let's turn this into yogurt ID to pudding ID, because we want a mapping between these IDs. Yeah, and the yogurt. Okay, so a fun builder. We also need the body builder. That we are going to create right now. Up here. Let's actually go into the yogurt, or maybe the yogurt to waffle thing, because up here I would have assumed there was like a yogurt something builder. Waffle fun builder. Where are these? Oh wait, these waffle builders and so on, they're defined in here as well. Oh, that is interesting. Well, sure. So we'll need something similar to build a pudding fun. We'll have the expressions, and for the body we'll have the local expressions. We'll just have expressions, which will be a list of IDs. Hang on, in the yogurt we have something similar, I think. Don't. Oh. Here the builder is defined in the conversion file. Well, it's kind of a mess, I guess. Yeah, this is more like what I want, I think. Okay, so we have a code compiler show, we have a fun builder. runtime stuff? Sure. And this just works on the fun compiler. Oh, and passes the body as an extra thing. Sure, let's do that. Oh, let's do something similar. We have a pudding fun builder. Right, yeah, this is constructing pudding. Boom. Pudding has a bunch of functions that should be compiled. And to build a function, you can create a pudding fun builder. Pudding fun builder. Let's see. Pudding fun builder just maintains a list of expressions. And then in there you have pudding body builder. Makes sense. So you can create a pudding fun builder where you just pass in the number of arguments. Maybe? No, not really. No. That just returns you an empty list of expressions. Makes sense. You can create a pudding body builder. It stores a reference to the pudding fun builder. So this pudding body builder has expressions, which will be a list of pudding IDs, and it stores the parent. Yeah. So then on that body builder, you can say push this pudding expression that will give you a pudding ID, because it will construct one where the index will be builder parent extras.len, and then builder parent dot extras.push expression, like that. That doesn't work. This does work, yeah. And then you can do something. Yeah, what can you do? You can use this pudding ID. We just return that ID. And we also append this ID to our current body. So, like this. Yeah, and then on a pudding body builder, you can say, hey, please return this. And that gives you a pudding body, because that's going to be a pudding body, where that is returned. Let's see if that makes sense. Pudding body has parameters. And expressions. And returns. Okay. So here the pudding body builder also needs params. And here you not only have push, but also push param. And that does the same thing, just, yeah, let's add a push on the, not push, but I guess create on the pudding fun builder. And then these can use that builder.parent.create pudding expression.param. Yeah, and down here we say builder.parent.create that expression. Pudding expression is not an enum type, true, because that's a struct that contains both the kind and type. So this also needs a type. Pudding expression with the kind, pudding expression kind param, and the type that we were given. Maybe not like this. Pudding op is what it's called. That is much shorter. I like it. Okay, yeah, and this returns pudding body, and params will be very similar to expressions. Cool. Yeah, and in the end we can finish the pudding fun builder with a body by creating pudding fun. So let's look at that. It has expressions. Let's say it doesn't have this, because I want to turn captured things into explicit arguments here already. Yeah. Cool. Similar to how we did that when compiling to C code, by the way. So putting body builder, the params field is missing. No problem. Just create it like that. Yeah, this. Oh yeah, we are in the function builder already, so here we have, yeah, we finish this giving us expressions and the body. Nice. We should also be able to get a given ID from get an expression given the ID. So if we have a pudding fun builder and an ID, we should be able to get the corresponding expression by just taking the builder expressions and getting the index that the ID points to. And yeah, that returns a pudding expression. And same should also work, I think, for the body builder, because that's the main way that you interact with that. Like oftentimes I think you'll just have a body builder and not care about the underlying function builder. So for convenience, I'll also have a builder.parent.get that ID, calling this other function. Okay. Yeah, on a pudding function, we can also directly get the corresponding expression. Yeah, pudding IDs, they can be compared and stuff like that, sure. Yeah. Okay. It's got still. Okay, yeah, this is nice, I think. Very nice. Oops, sorry about that. So, converting yogurt to pudding. Down here, let's start at the bottom. We build a map from pudding signatures to pudding funs. That makes sense. And then we create a pudding. Perfect. And we can map all of these yogurt funs individually. Yes, also makes sense. With a pudding signature and oh, it's called still one there, maybe. Well, and we just turn that yogurt fun into pudding. Nice. So this happens down here, up here. When you call a fun, oh yeah, no, we don't do anything stack-like. Instead, we say, let's see, to pudding of a fun means we create parameters, which are some yogurt IDs, sure. What do we need them for, though? I think we don't really. Yeah, I think we don't. Yeah. Oh, you know what? Let's remove this. Hang on. This function pointer as well. You know, the yogurt types, they were recursive. In here we just have opaque pointers. That is crazy. So these types are no longer infinitely big, which makes sense. Yeah, maybe they should be typed. I don't know. Okay, you know what? I'm gonna just comment this out, and we'll get to that when we get to that. So parameters is a list of IDs, I guess. and then for each of the parameters we push a parameter in here. Okay, here we get the types. Oh no. So if the function oh yeah, no, let's not do this. Let's say that if the function captures something, then we also have an additional parameter in here. Yeah, and we don't do any memory layouting at this point in time. So nothing of that. No, let's fix this up here. So if the fun captures something, then we have an extra parameter. Oh, look at this. A pointer to the closure. This looks pretty clean, actually. And then each existing other parameter also becomes part of this right here. But actually, let's move this up here. Boom. I want to create a pudding fun builder with nothing. I think this needs nothing. And then instead of saving the parameters like this, we can just say, fun builder push param of this type. I'm not sure. These are these types, maybe. Clean. Clean. Yeah, we'll also have this. Yeah, and if the function captures something, then we do fun builder dot params get 0 is the closure pointer. That's just an ID. And what we do is we push expressions. So we say fun builder. Oh, hang on, we create a body. Is fun builder dot body builder. And then we can say body builder, please push we need to do that anyways. Let's do that up there. Let me check something. Bodybuilder, yeah, accepts a mutable one. That is correct. Oh yeah, and this really just does. Oh, let's call it builder because this is the more the builder that does all of the stuff. And the fun builder is more like a separate. No, just this holds onto the expressions, but that's it. So in the body we push parameters for the closure and all actual parameters. And if the fun captures something, then though. But I think this is just an ID or something. Something like this. And here we need to get the type somehow. And some captures. I think this is, let's say, closure pointer equals, yeah, and then we switch on the fun captures. Yeah, and then here we can say that. And then for each, ID in the captures, we basically do well, oh yeah, in the pudding we also need operations for dealing with memory, for dereferencing some pointer. Ooh, and this kind of... The thing is, this... this needs to know the type of the pointer. Oh, hang on, but because this yogurt op is in an expression, we know the type of the resulting thing. Okay, yeah, that's fine. So for ID and captures, do yeah, okay, first we dereference the closure pointer. Oh, we don't have any syntax for creating an expression from an op and a type. I think I'll add syntax for that. Yogurt. Here we had the $sign. Let's use that. Oh, this one. So pudding op and a pudding type can be converted to a pudding expression. Nice. And then in here we can just say that. Oh, and down here there was something similar. Yeah, here. We can say pudding op using this type. Amazing. Okay, so we know that the type of this is, well, here we kind of need to calculate a pudding type for the closure, which will be some sort of struct, I guess. With fields for every capture variable, or something like that. I'm not sure where that is though. Oh. struct maps string to pudding ID. So for every ID in the captures, with naming, but sure, we just put that ID into the captured thing. The index will just be that, and the item is probably something like a type, hopefully. Yeah, this is what we need to insert there. And okay, after we did that, we can then dereference the closure using the closure type, which will just be a struct with the captured variables. Look at that. That is kind of amazing. So we dereferenced the closure. And then for every captured variable, we just get the corresponding field from the struct. Like, yeah, member off with an ID and name with a string. Off with an ID and name with a string. And the string will be the ID. And this entire thing has the type, you know, this part right here. Yeah, let's move this out of there. And then in here we can just do captured name to type, get that. Amazing. Okay. Now we have, so what we do at the beginning of every function is, well, we get the parameters, and if there's a closure as an extra parameter, then we also get all of the, we kind of dereference the closure pointer, load the closure, and then get the individual things from the closure out of there. Yeah. Oh, hang on. And then we add that mapping as well. Okay. Where's that? Yogurt ID. ID to pudding ID. Put. That. Okay. And that was basically this. Amazing. Okay. So, what next? Yeah, this we don't need to do. Converting a function body to pudding. Yeah, we do that. Using the fun, using the function builder, using the builder, using the yogurt ID to pudding ID. And in the end we finish the function builder using that body. Okay. So, converting a body to pudding. What does that do? It creates a new body. I see. Let's maybe, I'm actually not sure. Let's hang on, where body is used. Yeah, the pudding fun has a body. And then several, okay, the switch also has a body. I see. Yeah, so we kind of want to add the, we don't want to create a new body builder. That's for sure. Well, you know, sometimes we do for inner bodies, but not for the actual function body, because we already created a builder for that down here, and we did stuff and pushed stuff to the builder here. So only up here what does this do even? Creates a new builder, and then it returns that. Sure. You know what, let's copy this part. Not elegant, but I know, but no. Let's copy that down here. Just say fun.getID, convert that to pudding using the fun builder and our builder and this and this and that. Boom. And do that with the fun body. And then put that in here. Sure. And then get the final body by saying builder.returns that builder.finish using the body. Okay, yeah. And up here, this doesn't need a body builder because it constructs a new one. And then for every ID in our body, we get the corresponding expression, convert that to pudding, and that results in a pudding ID. This, of course, being the yogurt ID. And in the end, we return that. Okay. So I think we should now be able to convert a body to a function, but of course we can't, and we don't convert individual expressions to functions yet, to expressions yet. So an expression within a function should be able to convert that to pudding. Here's a fun builder, here's a body builder. Amazing. Actually though, the body builder contains the fun builder, so there is no reason to have that in there, I think. Okay. Yeah. And we also have this mapping here. Sure. Then what we do is we switch on the expression. Makes sense. Param is not reachable, uninitialized is not reachable. Values, we kind of have to convert these to pudding. Like to do. Structs, we don't memory layout them yet. Oh, well, kind of. No, we don't. We just, I think structs map to pudding structs one-to-one. So here we can just say, build a pudding dot struct, which accepts a map from string to pudding ID. So we can say struct has yogurt struct. Yeah, that's just a map. That is what I expected. So for every field, we just naming is difficult. We do this, we say fields, put, this is, the key is a string, the value is an ID, and we know that this ID has been lowered before, so we can do yogurt ID to pudding ID of that ID. Okay, yeah, and then we just create the struct, that's it. Like, this is trivial, Okay, so members. Case member. Actually, members are pretty much the same thing, right? We don't need to do anything, we just yeah, no memory layouting necessary. Oh yeah, here we need to map the type as well. So putting op dot member member is putting member, which has an off, which is this. And it has a name, which is the member name. Yeah, okay. That is easy. To be fair, later on this will be a bit more complicated because we'll also add dupe and drop instructions for each of these expressions. So yeah, right now it's basically a one-to-one mapping, and yeah, except for lambdas and yeah, pretty much lambdas, I think, and variants, which can be recursive, so we have to think about when to put values on the heap. Oh, hang on, I'm just mindlessly copying that from up there. No, variant has something else. Variant has a name, I think. A symbol, sorry. And payloads. Yeah, okay. Bodybuilder doesn't exist. Well, that is weird. Gonna check that out later. Okay, yeah, switch. Oh, hang on. Yeah, hang on. Some of these payloads may need to be pointers. Put them on the heap first. Okay. Oh man. Okay. Yeah. Yeah, I'm gonna take a break.
Well, that got way too complicated. I got kind of stuck writing the pudding. So I refactored that last night. And what I did is I literally copied the yogurt definition and renamed yogurt stuff to pudding stuff. You can even see that it even still contains the yogurt values. Like everything is just very similar to the yogurt, except there were two additional instructions, two operations, dupe and drop, which increment and decrement the reference count of a pudding expression. Because in the pudding, every single value, every single value is conceptually reference counted. In reality, that's not the case. In reality, we'll only reference count heap allocations. And if you have a value like a point with x and y as fields, like we don't need reference counts for those. We just store them directly in line. And if you pass the point to somewhere else, we just we just copy the entire point. We don't need to keep reference counts and pass pointers around for every single value. But still, conceptually, it's a lot easier if we treat every value as being reference counted. And yeah, mapping the yogurt to pudding is then quite trivial because they are literally the same, except the pudding also has dupe and drop. So I commented out all the code that was here before. I still believe there is some value in having some sort of C-like type level, but I think that should be maybe a separate compiler stage after the pudding. So between the pudding and waffle, I may get to that later, but for now it's not a priority, I think. Yeah, and you can really see that just here on the minimap on the right. This commented out code was like really, really big. And the current code in here is like 100 lines or something. Yeah. A good 100 lines. Like that's not a lot of code. And that makes sense because the mapping is trivial because they are on the same abstraction level. So the yogurt contains functions, and to construct a pudding, we just map each individual function to pudding and put them in a map, and that's it. And mapping functions is similarly straightforward. We create this pudding fun builder, we create a mapping between yogurt IDs and pudding IDs. The captured variables, well, if the function captures none, then we also capture none. Otherwise, they are mapped to, the two parameters of the same type. And yeah, what else is there? We have the body, the function body, that is mapped by converting this body to pudding, and that's it. That's everything needed for mapping a function. So next, converting a body to a pudding body. Similarly straightforward. We just create a body builder, we go through the parameters, add them to the body, we go through the IDs of expressions, add those to the body. Yeah. And this is different. I'm gonna get to that later on. Yeah, and expressions are similarly like, for example, if you have a struct, we create a pudding struct. If you have a member expression, we create a pudding member expression, and so on. The only difference being that we insert these dupe and drop instructions at some points. So the semantics are, once you exit a body, those values go out of scope, meaning they should be dropped. And that's what happens right here. All the values that this body owns, for lack of a better term, aka the parameters and the actual newly created expressions within the body, they are dropped. So we push this pudding op.drop of this. And the type is, this expression is never used by anything else. So
I just put plum type.never there. I'm not sure if that's, semantically it doesn't really, it's not like a return expression or break or, well, we don't have them, but something that, or a crash or something that actually never returns. This does return, this does complete this expression, but it doesn't return anything useful, and you can't do anything with that. So I use plum type.never for now. The type should never be used anyways, so it shouldn't matter what we put there. Okay, and yeah, I mentioned that we drop all expressions. Well, before we do that, we dupe, aka increase the reference count of the expression that is returned, because we want to keep that. We don't want to garbage collect that expression. And similarly, for the instructions, they also insert dupe operations for the values that they depend on. For a struct, for example, for every field that gets put into this struct, it pushes a dupe expression. For the member expression, it pushes a dupe expression of the member. For the variant, it pushes dupe, like creating an enum variant thingy. It dupes all the payloads. A switch dupes the condition, and so on, and so on. Yeah, but this is pretty straightforward. So yeah, let's maybe look at how the pudding looks like. I think let's print the pudding and not do this part down here, maybe. Well, I don't know. But I also added these print line things to see, so that we can see where the compiler is doing what. I should really add a make file to Plum, I think, at some point. Well, okay, compiling the compiler, then egg takes a lot of time, but well, yeah, this is the thing. We see that compare ints, for example. We assume that these ints, we take ownership of them, but you can have, ownership is kind of like you are responsible for decrementing the reference count of that value if it goes out of scope when you're done using that. That's what ownership means in this compiler stage. It is similar to ownership in Rust, where that concept also exists, but different in the way that you can have multiple ownerships of the same value. It just means that both of these, multiple pieces in the code are responsible for decrementing the reference count when they're done with a value. And these function parameters that you're given, you take ownership of these. So let's say the reference count of these ints is 1. In reality, ints are passed as values, not as pointers to the heap, so they don't have a reference count, but let's ignore that. Like on a semantic high-level view, let's say these are values that have a reference count of 1. Because we use them in this kind of built-in instruction thing, and we basically call this compare ints instruction, the compare ints instruction should take ownership of them. The compare ints instruction, similar to us right here, it will drop these values when they go out of scope, when it's done using them. So before we call that, we need to dupe the values. And this returns something. So yeah. Then we have this right here with, let's say initially this reference count was 1, and this the reference count of this was also 1. Using this, the reference count of these would be 2. Compare ints decrements, it takes ownership, decrements the reference count of these. So after this, the reference count of these two is 1 again. It was 2 here, then this drops the reference count, it drops them, so the reference count is 1 again. And by default, the reference count of a newly created value is 1 as well. So reference count 1, 1, and 1. And now we want to return that result, this value. So at the end of the scope, we drop all local variables, the 0, the 1, and this 4. But because we want to return that 4, we also dupe that 4 before dropping it in the body. And yeah, this is like highly inefficient. You can do much better things. You can, for example, just call this function and that's it. Because duping the reference count of 4 here and then dropping that later on basically increments the reference count and then decrements that. That doesn't, like, you can remove this and you can remove this. And duping the 0 here so that we can pass it to this and then afterwards dropping it, well, we can just remove that and with this dupe in front and this drop at the end and just give compare ints the ownership of 0, and then compare ints will take care of freeing that int. So in reality, when we optimize this code later on, we will have no dupe or drop instructions in this function. And that's actually the case for many functions. As long as if you have a complicated expression in your source code, like 2 plus 3 times something else, and let's say you have not just numbers, but you have big heap allocated things as well. You have some list, you pass it to the append function using another item, and the append function returns you a new list, and then with that list you map that to something, and you have complicated control flow. Most of the time your usage of values will be linear, meaning the reference count of these values will very often be 1. Sure, if you put things into a struct multiple times, that's like in general, if you define variables and then you use those variables multiple times, you will need to really do reference counting, and the reference count will get higher. But for most values, for most like intermediate expressions and so on, the reference count will just be 1. Meaning that we can optimize the code for that. Like a lot of these dupe and drop instructions here, they just get removed. They will just disappear. And having the reference count around also allows us to do some nice optimizations. If we have a big list and we append something to that list, like a big like actual buffer in memory somewhere, however we might represent that. When you say, please append something to that or change an item, semantically in Plum, values are immutable. So we would have to return a new buffer, return a new list with that one value changed or appended. But in reality, we can just check, is the reference count 1? If so, then we'll just change the value inline. So having reference count not only is sufficient for precise garbage collection, but it also means that we can apply many optimizations. All right, let's maybe look at an example with nested bodies. And my voice is giving out. Well, this is equals function, sure. So we call some cast functions, and again, before every call, we just dupe the arguments, because the call is responsible for dropping the reference count of that value. The call takes ownership of that value. And similarly here, and then similarly here, then the switch condition again. And within these bodies here, you can see that we drop these intermediate expressions before returning. And I think this, these dupe and drop operations, it was pretty trivial to insert them. You literally go over the referenced IDs of an expression and you insert dupe instructions. And at the end of the body, at the end of every body, you just drop all the expressions. But that should be enough to, implement reference counting and garbage collection. So let's look at what we do from here on out. Let's maybe not print the pudding, but instead just compile this to waffle and then print the waffle. I kind of started working on this. In general, we had this yogurt to pudding, yogurt to waffle file that mapped yogurt to waffle. AKA, it uses, it memory layouts things, it uses those memory layouts to do some crazy stuff. It's not a lot of code, it is reasonably concise, I would say. But now we would basically have to change that so that instead we map the pudding to waffle. It should be pretty straightforward because there was a tight, the pudding is almost the yogurt. So I just copied the yogurt to waffle content into this file and then adjusted that. And yeah, a lot of that is just very, very similar with just renaming yogurt to pudding, and that's about it. However, there are these two new operations that we need to support, dupe and drop. And maybe let's, as some sort of placeholder, let's say these don't do anything. They just push nothing. They are just an empty expression. They don't return, they don't evaluate to anything. Yeah, you can see that this looks somewhat reasonable. I'm actually wondering, where this is the waffle. Yeah, hang on, you don't see anything. You don't see dupe or drop things. I would have expected to see, waffle padding stuff in there. Ah, man. Okay, converting a body means that we create a local expression by converting that expression to the waffle. That means that let's maybe, okay, yeah, exactly. We don't want to convert the yogurt to waffle, we want to convert the pudding to waffle and use that. That's what I get for not paying attention when uncommenting code. Yeah. Yeah, that's more like what I expected. This code is still correct. It still compiles, it still runs perfectly fine. But now we have these extra padding things in here. Because the dupe and drop instructions, they are just converted into these operations that do nothing. I actually think in the next compiler stage, these padding of 0 instructions, they get removed. I'm not entirely sure about that. But anyways, what am I trying to say? What am I doing here? The point is that we need to do something more useful than mapping these to padding. We should instead actually increment and decrement the reference count of values. Now the thing is, values don't really have reference counts. If you have a point containing an x and y coordinate, that doesn't have a reference count associated with that. Only heap allocations will have reference counts. So I think the way to go about that would be to generate functions. Generate a function for duping an int and dropping an int. And those functions don't do anything. But you also have these functions for types with pointers. like recursive types. If you have, we'll have some function dupe of a linked list. And that would basically go through the list enum. It would have to switch on that, see, oh, is this an empty list? Then we don't need to do anything. If this is more, then we'll, it contains a pointer, and we'll go to that heap allocation and increment the reference count there, and that's it. So basically, for every, even though not every value is actually reference counted, we'll have dupe and drop functions for every type. And we'll just call these dupe and drop functions, and they will do type-specific things. For primitive types like ints, they don't do anything. For structs, they will call, dupe will call dupe on every struct member. For enums, the dupe function will switch on the enum, and then depending on the variant, it will call dupe on all the payloads. So you might wonder, like, where's the value in that? And the value is that for some of these types, like enums, for example, recursive enums contain pointers, there we can detect that. And instead of calling ourselves recursively, saying, well, dupe this other list, we just increment the reference count of that pointer. Of that, in the heap allocation, there's literally a value, the reference count. Yeah, that's kind of like a rough plan. Sorry if that wasn't explained super well. But I can maybe show what I got so far. I commented out something in the dupe drop thing. Yeah, right here. I started implementing the dupe function. So what we do is we compile a type-specific dupe function, and then we call that function with the value we want to dupe. And because this function returns nothing, it returns something with a size 0, alignment 1. Yeah, kind of weird that we don't have to, like, this is not obvious what this does. But yeah, waffle call. So the question is, what does this compile dupe fun does? And this is something that I defined way up top here. Yeah, compile dupe fun. Yeah, so it can be. This is supposed to return the signature of this function and add the function to this funs list. So the signature of these will just be dupe and then the type name. I think this shouldn't conflict with any user-defined function because those can't have spaces inside. And if that function already exists here, we're done. Otherwise, we put a placeholder so that if we have a type, like a recursive type, we don't recursively call, like, generate these dupe functions. It's enough if we generate that function one time. So we just put a placeholder in here, and at the end of the function, down here, when we have finished creating that function, we put that function in this mapping and return the signature. Okay, so how is the function actually created? What we do is we memory layout that type, and we create a waffle fun builder that will return, that will accept that thing as an argument. So as the thing with waffle ID 0. Yeah, so we have a waffle builder, the parameter passed to this function implicitly as waffle ID 0 with this, memory layout. And then depending on what kind of type that is, we do different stuff. For primitives, we do nothing. For never, we do nothing. For structs, we want to dupe all the fields. So we memory layout the struct. For the fields, we basically create this operation, push that on the body builder, a call to dupe of that field. So field here is the type. I think fields, on the type level, fields is a map from string to the field type. So this right here will be the field type. And we compile a dupe function for that type. And as an argument, we pass the member of accessing on the parameter the field at offset at the offset of our field. Yeah. And this seems pretty low level, that we have to care about memory layouts and sizes and so on. So again, I think it may make sense to insert another compiler stage later on between the pudding and waffle, where we kind of have C-like types. But right now I just want to get dupe and drop reference counting working. And yeah, we can, I think right now the complexity of this compiler stage is quite manageable. So I'm fine with how it is right now. Yeah, for enums, we kind of build that they get compiled into, hang on, not this, but oh yeah, this, into a switch, where we switch on the enum tag, and depending on that tag, we do, what it says in these cases. Cases is defined up here, and for every variant, we push something to that cases thing. And what we do within these cases is what? Yeah, hang on. We want to increment the reference count of an enum. So what we do is we switch on what kind of enum that is, and then for every payload, we want to increment the reference count of that. We want to dupe that. And yeah, what it does is, if the value is stored directly in here, directly in line, then we'll actually just call dupe on that thing. But if it is indirect, if it is a boxed payload, then we literally want to read the reference count from memory, add 1 to that, and then write that reference count back. And then we're done. We don't, if you have a huge linked list or something, and you dupe that, we don't want to traverse the entire linked list. We just want to get the, traverse the thing up until the first pointers that point to heap allocations, and then we just increment the reference count, and that's it. We don't need to visit the rest of the data structure. Yeah, so yeah, I'm not entirely sure what to do here. And this is kind of where I stopped working. And which is also why I think, no, it works, hang on. Let me maybe recompile that. I think this should fail with this to do. Yeah, dupe boxed enum payload. That is where I got kind of stuck. All right. So really, every pointer that we have points to a heap allocation. And at that heap allocation, we don't just store the the data itself, but we also store a reference count at the beginning. Yeah. So that means we need to change all the code that interacts with the heap. Yay. Add an offset of 8 or something like that. So that in here we can kind of read that heap value and then add 1 and then write that back. I'm actually not sure if we have the capability to do that in the waffle. Let's see. What kind of heap stuff do we have? We can, we can't box something. Oh, here. We can box something, aka put an expression on the heap. We can unbox something, aka get an expression from the heap. But we can't really change heap memory. We can only, like this, sure, this sets the memory there, but it also allocates new memory. So we can't change memory that we have allocated. That is kind of unfortunate. So I think we'll need some sort of write. Yeah, waffle. Not entirely sure. I mean, loading a value can be done using unbox. First of all, let's go with load and store. I think that those are more fitting terms. And yeah, I mean, unbox is kind of load. And box is kind of allocate and store. So, you know, the terminology is kind of weird. I think box and unbox, they make sense if that's the only two operations you have. If you also have writing to memory and stuff like that, this is kind of, the terminology doesn't fit. So I'd rather use load than unbox. I think that's also way more, you don't need to know about the term boxing, which is a kind of very specific, weird term. So load is a lot more intuitively understandable. And rather than box, let's call this maybe create, allocate, I don't know, create some sort of heap value, some heap object. Yeah, you can load that object, you can load something from that pointer, you can store something to that pointer. I think storing is actually a bit more complicated. We'll need, waffle store, because we'll need two things. We need the pointer, which will be a waffle expression. Yeah, and we'll need the actual value to store there, which will be another waffle expression. Yeah, so waffle store is actually a bit more complicated. Great. And we'll also have free, which just accepts a pointer. We could also pass a size in there, I guess. No. You know what, let's maybe also add like, comments in here. I'm not entirely sure how these call stuff, arithmetics, to kind of give this, section stuff, binary, like bitwise operations, memory, arrowing, yeah, and there's like general stuff, I guess. Okay. Yeah. Yeah, I think this is fine. Not just fine, this is pretty great. So I'll also add, rename these create this expression, allocates that and puts that on the heap. And that calls create. Similarly, there will be waffle 3 of an expression, and we'll have exactly this. This should be a pointer. And what it does is it returns a waffle expression with size 0, alignment 1. Yeah, the kind being waffle expression 3 of that expression. Yeah. Amazing. And then this will just be renamed to load, but otherwise it's pretty much the same. And waffle store will accept pointer, and this will result in a waffle store. Pointer is the pointer put on the heap, and the actual value is the value put on. Now, what is value? Oh yeah, it is defined up there. Okay, and that results in a waffle expression with size 0, alignment 1. Amazing. Okay. Yeah, down here, rather than box, we have create, I think. And this is load, and similarly we'll have store, and we'll have free. Free and store, giving us a store with a pointer comma, yeah, and then the value. Cool. I'm just going through this, seeing where, I mean, okay, a new line, like which kind of changes I made to this file. But I think this all seems, yeah, this seems pretty reasonable. Oh yeah, this is nonsense, and not nonsense, but yeah, we don't have, I'm just gonna remove it. There was just some brainstorming thinking stuff. Okay. Yeah, I think the waffle is equipped to handle heap allocations and reference counting. You know, it has new load and store operations, it has new free operations. So really the only thing remaining here, oh yeah, waffle to bytecode, we still need to fix that. But before we do that, I'm gonna finish this. Yeah. Okay. Yeah, so what this does is, basically we want to do a waffle store. And a waffle store accepts two things. It accepts a pointer, and it accepts a thing that we want to store there. So if this is boxed, then the pointer will be this right here. It will be a member at payload position.offset and size, 8, alignment 8. And right into that pointer, we want to store an int. So what we want to do is we want to actually store a waffle add of loading that pointer. So pointer waffle load pointer. I think it works like that. Kind of like that. Now, so what we want to do is we want to load from that pointer here 8 bytes, aka an int, aka the reference count that is stored there on the heap. We want to add 1 to that. That doesn't work because, let's see, waffle, yeah, we have aggregate, we have word. Indeed, it's called word. Yeah, sure. Waffle word, we add 1 to that. And then we store that back into the pointer, back on the heap. Yeah. And this is all that's needed to increment the reference count. Amazing. I like that. Okay. Yeah, let's just compile this and see what happens. Fair enough. All the box and unbox stuff needs to be changed. Box is now, let's change all of these to create, and waffle unbox like this one right here. And let's change this to load. Yeah, yogurt to waffle. Hang on, how everyone compiling main to waffle of pudding? Why does it even call yogurt to waffle? Oh, because to waffle of yogurt value. Yeah. Yogurt, like again, because the waffle is literally, because the pudding is literally basically a copied version of the waffle, the pudding still contains a yogurt value in here. And this is something we'll need to change, change before committing. This should have, like, we need to do something about that. That means that, yeah, in general we use this code, but there's also this one function from, converting yogurt to pudding, hang on, yogurt to waffle, up here, that we use. And let's see, yeah, this one right here should rather be waffle create. Okay. Hey, waffle to bytecode, sure, I agree, that is not working yet. Because there are new instructions and I don't want to deal with that now. So, rest of the pipeline. I'm just gonna, well, actually, waffle to bytecode is what we still need to do. Oh, okay, so the part in front of that actually worked. That is not surprising, it is nice. Okay, let's see. Let's look for some dupe functions. Here's a dupe function, duping this enum. What do? We just switch on the enum tag and we don't do anything there. I mean, yes, that is certainly what you can do. Again, optimizing this should be done, but nice. Okay, here we have an enum that is either empty or it's more with an int and another enum inside. This is only this part is the recursive enum. Okay, so we switch on the tag, sure. Yeah, this is size 26, so the tag is at offset 25, size 1. And switching on that, if that is empty, we do nothing. If that is more, then we dupe the int, and we dupe this recursive list thingy that is stored in there, that is stored in line in here. Makes sense. Now the interesting part. Yeah, this one right here, duping a linked list item, or like a linked list. What we do is we switch on the tag. If it's an empty list, we don't need to do anything. Otherwise, we dupe the int. Makes sense. And then we do this. Okay, so hang on. The int is at this enum, offset 0, size 8. Yeah, makes sense. And offset 8, size 8, is the pointer to the next list item. More contains the int at offset 0 and the pointer at offset 8. So what we do is we load that pointer at offset 8, size 8. From that memory location, we load 8 bytes, the reference count. We add 1 to that. This is just a 1 stored in 8 bytes, so like an int, We add those two. Yeah. Okay, and then we store that incremented reference count back in memory. That is pretty amazing. Okay. Damn. That is cool. Let's see what else happens here. Yeah, this is not super interesting. Hey, here's the dupe int that we called below. It just does nothing, which makes sense because int doesn't contain any pointers, so there's no reference count to be increased. That is amazing. Damn. Okay, I really like that. Yeah. Cool. So, yeah, one thing I should note is, will this work? Probably not. Yeah, I should maybe work at two things. Okay, before I even go into drop, I need to adjust the way that things are stored on the heap. Because while we assume that the reference count, that a heap allocation always contains a reference count at the beginning, it doesn't really. We just read some random data from the thing that's stored there and modify that. That's not correct. So when creating values, we actually need to make space there for the reference count, and I guess set it to 1 initially. So that's something that we need to do. And also I want to see that blowing up before. So I will implement this right here, aka converting stuff to VM bytecode instructions. And that means these bytecode instructions, they already support storing and loading stuff. That is nice. Let's also support free, hops,
a pointer, I guess. And address is returned here. Freeze the memory there. Yeah. And yeah, there are more invariants that we should document, that, you know, like this should only be an address that was previously allocated and stuff like that. Yeah. And let's see, switch instruction. Where are we? Oh yeah, this is the main loop, the main instruction loop. Yeah, currently that's just not do anything. Like we don't actually free values, but that's fine. And in general, in Martinez, the concept of freeing memory is kind of complicated. Okay. I think that's actually enough to, like, oh yeah, this needs to be adjusted as well. We have malloc. We have free, which just takes the pointer, frees it, and that's it. What's going up here? Yeah, we need to enter free. Down here, we have probably changed the names of these. Yeah, because this is waffle stuff. So the box thingy is now called create. Apart from that, nothing really changed. The unbox thing is called load. We also need some sort of store, and we need free. Let's do the free thing first. So freeing a pointer. I mean, that's actually pretty doable. You're padding before data. We just align the stack to 8 padding before pointer. Yeah, we align the stack to 8 bytes. We push the pointer. I'm not entirely sure where we do that. Hang on. Oh, similar to this right here. Yeah. We by construction push 8, of the pointer. Oh, and the pointer is probably, oh, it's a complete, like waffle thingy. So we need to compile that, really. Yeah, that makes sense. So what we want to do is not push the pointer directly. We're going to say pointer compile. Yeah. And this will cause the pointer to be on the stack. And then what we do is free that pointer. Yeah. And afterwards we want to pop this padding. I mean, let's just call that padding. I think it's not like this is a giant enum case, I think. Yeah, this is fine. Okay, so we pad the stack so it's aligned to 8 bytes. We compile our pointer. That may be like a huge waffle expression. It may be, reading something from the heap, adding 1 to the reference count. No, that's not the place right here. But anyways, yeah, this seems fine. We free that and we pop stuff below. Okay. Okay, yeah. Amazing. Yeah, And we have load and we have store. Store is actually pretty similar to create, I think. Except we already have a pointer. We don't need to allocate memory for that. I'm not sure. It should make sense to it should make sense to unify that or share some of the logic here, because like, you know, just copying this down here seems kind of wasteful. Yeah. Okay, so what we do is, now let's see how the, I just want to look at the store instruction. Store. What does it do? Store, it pops an int, pops an address, stores int to that address. Okay, so the int should be, the actual data should be on top of the stack, and then there should be the address. Sure. Compute the data to be boxed. Yeah, this is a store, and a store has data, value, I think. Yeah. Let's see. Waffle down here. Yeah, pointer and value. So we kind of compile the value that we want to store. Seems reasonable. That is the data start, sure. Then we have padding after. We align the stack to 8 bytes. Yeah, we don't need to allocate anything. Compute the pointer, I should say. Yeah, pointer start is build a stack size. Okay, sure. Then instead of calling malloc, we compile the pointer. So store.pointer.compile. Using the builder. Push 8, push 1. Yeah. Let's see. Store.pointer.compile. Okay, hear me out. Easier approach. Instead of create, let's just say malloc. And waffle expression will be the size. So we have malloc and free and load and store. Yeah, and rather than, if you want to create something, you just do malloc and wrap that in a store where you store the value into that allocated stuff. That seems more reasonable. And then in here we don't have this code duplication of a store and create being so similar. Yeah. Okay, so this, no, it doesn't do that right here. Nope, it just compiles the pointer, which is 8 bytes aligned. Yeah. Yeah, we don't need to do this manually because okay, yeah, we may want to do that manually. Sure. Okay, the pointer is 8 bytes in size. So then we do this, copy the data to the heap. Yeah, I don't, like, I'm just gonna leave that edit as is. And up here, this create thing, instead I'm gonna call this malloc of some size. Oh, it doesn't have an alignment, but I think that's fine. Alignment is always 8. Yeah, sure.
padding before data is aligned to 8. Yeah, we don't have any data. Compute the size to be allocated of the memory to be allocated. Yeah, then size start is builder stack size. We compile the size using our builder. That is guaranteed to be an 8-byte thingy. Then we allocate memory. That's it. We don't need to copy anything. Okay, and we can probably condense this even further. Yeah, a waffle malloc is always aligned to 8 bytes. Let's just say that. I think that makes things a bit easier. And I believe that's the only thing we need in practice. Well, we don't need like size start. Is that even used anyway? Nope. That's what I thought. Like, this is pretty obvious code actually. And pointer start, we don't need that either. Nope. And we don't need that either, because this is already the size that's on the stack. Yeah. Pop below top, padding before data. The name is not really fitting, you know, it's just padding. Okay, let's see. We align the stack to 8 bytes. We don't need to do that because I think so. I think we don't need to do that. Assumes that the stack is already aligned for the expression. And malloc results in an address that is supposed to be aligned to 8 bytes. So we don't need that. So really malloc is just compiling the size. It pushes a byte for the alignment and then it calls malloc, which pops the alignment and the size, and that's it. Easy. Really, really easy. This is not a variant, okay? Waffle expression kind only has these variants, param padding, blah blah blah. Malloc is not a thing in here, okay? It is though. It does exist. Yeah, waffle create. That doesn't exist. Instead, we have waffle malloc of some size. That is supposed to be an int. So what we do is something like this up here. Int is word. Hang on. Yeah, okay. That is nice. So we can, even in here, we can just do is word. Oh, that is nice. That is nice. Oh, clean. Very, very clean. Okay, so the size. Oh yeah, I want basically this to be a word. This results in a waffle expression with size 8, alignment 8. It does malloc of the size. Okay, yeah, that seems correct. And next. Yeah, everywhere we use waffle create, we now have to change the code. And that's a lot of places.
presumably. So yogurt to waffle. Oh, maybe not. Yogurt to waffle, called waffle create. Really, what we want to do is, well, variant.payloads.get index.toWaffle. And this is the value, and then we want to store that value on the heap. So what we want to do is waffle store to the waffle malloc of that value's size. Well, you know, of a constant size, which is the value's size. And there we want to store the value. Yeah, this call doesn't work. Okay, it does now. Perfect. There are no definitions named waffle box. Waffle box, waffle box. Yeah, true. Waffle create is nothing. Yeah, I guess creating a helper function for that would also be nice. Yeah, let's do that actually. Let's do that. Waffle box. Let's not, you know, these waffle prefix things, they are kind of constructors for waffle expressions, and waffle box doesn't exist. So instead, I'm going to create a boxed thing of an expression, which will return a waffle expression, and this will do the general thing. It will allocate memory of the expression's size of a constant word expression size. Yeah, and in there it will store the expression. Yeah. And then in here we can say, you know, we convert that to a waffle. We want that boxed. Similarly here, we box that. Yeah, unbox is just called load, otherwise nothing changed. But also, like yogurt to waffle, we only use that one function, we don't care about the rest, I think. Let's just see where things fail. Inputting to waffle. Here's something red, I see that. Yeah, waffle create no longer exists. Instead, we just take that waffle expression, dot boxed. I should maybe just look for waffle create. Sure. Sure, let's fix the code in the comment. That's amazing. Okay. Yeah, printing waffle. Down here. Yeah, this is malloc. And this is the size. Amazing. Oh, that is painful. Switch cases. You know, having these assertions is so nice. Like, you really feel safe even when creating like memory, stuff that operates on memory and so on.
The program panicked. Okay, so we have a waffle switch. Yeah, switch cases have different size. Okay, yeah. Yeah, I'm not sure about that. Like what to do there. And the program panicked. To waffle of some waffle expressions. We don't know which one. Okay, so yeah, let's just log things and see where stuff fails, I guess. Yeah, compile drop fun. Oh, we don't even use that or do anything with that. Okay, so converting a waffle expression. Let's just print that. Compiling expression. I think I'm gonna make a bit of tea and yeah. Oh, this doesn't work because of stuff. Hang on, this is putting expression and we can't do that. Okay. That is unfortunate. Why not? I mean, I see we have putting up. Okay. Yeah, sure. Let's use the operation, and let's also, that needs a function and indentation. Oh man. Well, the op needs the function and indentation. Yeah, something like this should work. So we are compiling. I mean, yeah, okay. The switch cases. They just return. Oh, I see. So we're compiling this switch. Okay, fair enough. So what do? We compile variant empty. Okay. Yeah. Oh, this one. I see. And then a dupe and drop. Dupe 2, drop 2. Amazing. We compile this one, dupe 5, then we call some casts, then we have a bunch of drops. Drop 13 is the last one. True. And now we have this, where this is variant more of something. But these have the same type, right? That is what's confusing me. We probably do something wrong in here. I don't know. You know what? Let's just do better. Print better errors here. In here, rather than just panicking with that, we just print the expressions. I mean, why not? actually, let's put panic on the outside. And here create a string builder. And print that. And then for case in cases do you know, just print the case. And a new line in front of that. And in the end, we panic with the resulting string. And we probably can't print waffles directly. Oh, these are waffle bodies, I see. We can print, we don't have the waffle fun, I think. I'm not entirely sure. Yeah, okay, let's just debug print them and see where that leads us. Yeah. So these have different sizes. These two waffle bodies. Yeah, they have both have locals. This one is 234. And then returns 2, which is a waffle expression with size 17, alignment 1. Okay. And this one has locals as well. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And it returns a waffle expression with size 9. Alignment 8. I mean, let's be sure. Yeah, these are supposed to return this enum. This should have size 17. You know, the largest payload, the variant with the largest payload is this one. It has an int, it has a pointer, and the tag. So 8, 16, 17 bytes. But here it has size 9. So what happens here? Parts dot push. The first one should be this, just an int. Second one should be this, a pointer, dot boxed. Let's look at dot boxed. It is a waffle. Oh. Ooh, okay. So this does store the thing on the heap, but it doesn't evaluate to the pointer. Well. Is there like a waffle body or something we can just wrap around that? Not really, I'm afraid. Nope. Bodies are only for switch cases or you know, or the waffle fun itself. Okay, that is kind of unfortunate. So we can't actually do this. We can't just create a boxed version of a waffle expression. Because in order to do that, we need to have we need to use a local variable. We need to say, you know, first allocate a pointer. We need to say store something to that pointer. And then we need to say evaluate to that pointer. Ooh, that is not elegant.
I don't want to change the waffle too much. Maybe I'm just gonna add a to-do up there. To-do. Allow body, like multiple expressions in here. That wasn't really necessary when we didn't have expressions with side effects, like storing stuff. But now that we do have them, it may make sense to nest bodies in here. Yeah, okay. Again, I'm not gonna do that right now, though. Yeah, instead I'll just do something here. Do something about this. Let's maybe bring to waffle. Where's that used? Like how we say boxed. There were 3 places. Okay, in comment, fine. Then there was this, where we have access to the bodybuilder, where we can just create a new local variable for that and store stuff and so on. Okay, sure. And there was this one, again, where we can just create a new local variable and do stuff. Yeah. Okay, so I guess let's do that. That is kind of unfortunate, though. Yeah. Well, I'm gonna remove that and instead do something about that. So pointer is the result of calling waffle mel, and we're gonna store that on the builder, on the body builder. So body builder dot what is it, local variable for that pointer, and then we're gonna store into that pointer the expression, and then we're gonna return the pointer. Yeah, what is this though? Oh yeah, the expression is really this. Expression, let's call it payload. Yeah. Allocate memory for the payload size. We store that payload in on the heap, and then we evaluate to the pointer. Yeah. Okay, yeah, and we'll need to do something similar for the other case of boxed down here, where we want to store that closure on the heap. But we already have the closure. Now we're building a closure pointer by allocating memory. Yeah, we're storing the closure into memory, and then in here we just use the closure pointer. Oh man, this can be simplified to the waffle signature of that string.
Okay, yeah, payload.size is not a thing apparently. I think it is. There's nothing, oh yeah, for the values. Please let me have a bodybuilder. Okay, fine. Oh, that's actually pretty similar to the other one. Payload pointer, let's just copy that thing in here. And yeah, this is the okay. There were no definitions named waffle box. Indeed. Indeed, there are not. Yeah, let's see where this failed. This is mutable anyways. Yogurt to waffle. Oh. Line 31. Oh, hang on. Where did I paste that before? Oh, and down here somewhere. Well, yeah, no, that doesn't make any sense. Yeah, variant payloads.get index. Yeah, to waffle. Yeah, that seems right. Seems about right. Oh no. Yeah, and here we don't, that's it, here we don't have a bodybuilder. Yeah, it's, again, self-contained expression. It is difficult. It is difficult, I see that. Get to waffle. What is this? This is the signature to waffle of this value. Oh yeah, no. Now we pass around the bodybuilder as well. So yeah, for structs we do that, for variants we do that as well, for the payloads. And yeah, these, not even gonna talk about them. Oh yeah, that does mean that in here, for case comp time, here we need to pass the bodybuilder. Whew. Okay. Okay, pudding to waffle. 250. We have a waffle. Wait, hang on. We have a pudding ID. And we want to get the pudding ID to waffle expression dot get of that pudding ID. Yes. That returns a waffle expression. 316. Oh yeah, this is the closure pointer. We store the closure into the closure point. Okay, it compiles. That's good. Yeah, to do waffle to bytecode. I think that actually works now. Mostly. Right. Nope. Waffle to bytecode. And the store thingy. Store.value. Oh yeah. Mm-hmm. 316. Okay. That is actually nice. Very nice. Yeah. Of course it's not correct. Like this one, loads the reference count, adds 1, and then stores that again. But when creating a new list in, where's that, make list? Something like that. Make list. Yeah, here we do stuff. I don't even know what that is. We certainly do something here. I know, we call ourselves recursively. Okay. Oh yeah, oh I see. Yeah, when casting a more variant to the list itself, this right here. That should be where the enum, where the heap value is allocated. So let's look for that cast. Yes, this one. We cast this thingy, which is more of an int and a list. Meaning, because we know that this is more, this will actually be an enum with only one variant, storing an int inline, and storing this recursive thing inline. And we want to cast that to this enum. Oh yeah, hang on. We don't need... Is there another, yeah, this one. Okay, yeah. So we have an inline that is on the stack. You know, like an inline stored empty or more of an int and then list. And we want to remove one level. That to just, you know, empty or more of int and then a pointer. This means that this enum right here, that this inner list should be moved to the heap, and we should store a pointer in here directly. So let's see how that works. Okay, so we duplicate the tag, sure. We dupe the tag. Oh no, I was wondering, like, duping the tag doesn't make any sense. The tag doesn't really have type. But we dupe the entire value that we have here. That makes sense. Okay. Yeah, if it's empty, sure. Let's just, you know, have 16 bytes of padding and then a 0 in there. Otherwise, we'll have something else. And this is the interesting part. Not 16 bytes of padding and then a 0, but 8 bytes of something, 8 bytes of something else, and then a 1, indicating that this is more. Okay, so we dupe something, you know, we cast that to itself, sure. Dupe the int, no op, okay. We dupe this enum, okay. Thereby increasing the reference count of the inner, you know, inner thing. And then we allocate memory, 17 bytes. And we store this thing right there in memory. Eight bytes, hang on. Oh yeah, we store there the result of casting that enum. Okay. Okay. Mm-hmm. Yeah, and then we build another enum where the pointer, this newly allocated pointer where we stored the existing value, where that is directly in here. However, when we allocate memory, really we don't just want to allocate 70 bytes here. We want to allocate more. We want to allocate enough so that we can also store a reference count at the front. Which means in this putting to waffle, yeah, wherever we store something, we have these 3 places. Yeah, we'll also need to make sure that we do the correct thing with regards to the reference count. Okay, this literally just loads the reference count, adds 1 and stores that. That is fine. That is reference count aware. This one isn't, however. If we see, hey, this enum payload should be stored as a pointer, then yeah, we don't just want to allocate memory for the enum size, but also for a reference count that is stored at the beginning. And then rather than storing that value directly to the pointer, we want to store, well, that is actually fine, I think. A waffle, what is it, aggregate. How is that? Does that need a list? Yeah, that's nice. Sure. Yeah, okay. In that pointer, we store this aggregate thing of the initial reference count, a waffle word 1, and the original payload. And yes, this should be a list converted to a slice. Yeah. Yeah, that seems... Oh, well, waffle, what? No. Like this. We want to store to that pointer a reference count, 1, and then the actual payload. Amazing. And down here, for the closure, same thing. Same thing. We want to store a waffle aggregate of the, you know, a reference count and the actual closure. Okay, yeah, now we're talking. Okay. Let me take a break. I'm back now with some green tea. That is really nice. Yeah, next I want to look at dropping values. Like, I think the dupe stuff is kind of fine. So, dropping and freeing values. how would that work? Very similar to the compile dupe fun. We should have a compile drop fun. I think I created that just by copying the drop fun. Yeah, but that was some time ago, so let's just copy that again and then adjust that to decrement the reference count instead of incrementing it. Should be pretty straightforward. So, okay, the signature will be drop type. Okay, the boilerplate of creating a function with one parameter. Okay, for primitive types, we don't really need to drop them. Makes sense. Never is never reached. For structs, let's see, we want to drop the individual fields. Does that make sense? Yes, it does make sense. For enums, we want to switch on the tag, yeah. And then we want to drop the payloads of that tag. Okay, so we go over the payloads and we look at the boxing. If the thing is unboxed, then we'll just call ourselves recursively with the payload, like, call the corresponding drop function. But if it is a boxed value, then we want to subtract 1, like this. And if the reference count reaches 0, then we also want to free that. That is the additional stuff for dropping. I'm just going to add a to-do in here. Free allocation if ref count is 0. Okay, and lambdas, yeah, we'll look at them in the future. Okay, this is unreachable because we extend that type at the bottom, so we never reach the recursive marker, and we return nothing, and that's it. Okay, so far so good. Here we also need to call that, yeah. Here we say dupe this value, resulting in a waffle call. Dropping that value should do something very similar, except call the drop function for that type. Oh no. Okay, this is something I haven't ever reached, so this is interesting. Too many instructions. Well, look at that. Yeah, I guess let's fix that. Where's, what was it? 1024. Oh no. Wait. Is that? What does it say? Too many instruction builder. Dot instructions. .len. Okay. This is weird. This is super weird. Okay, I'm just gonna say 5000 and see if this works. Yeah, still worth it to do. Is that like, oh, I see, it rounds that up to the next power of 2 or something. Okay, I see, that makes sense. Yeah, okay, let's go with 2000 maybe, and dang. Okay, yeah, so we do not only dupe, but we also drop values. Yeah. So let's look at some of these drop functions. Maybe something. Yeah, this is the interesting one, and this is a simple one. Dropping some value just does nothing, basically. That is what I expect. And dropping this thing that that contains a pointer, well, if it's empty, then we don't do anything. If it's the more variant, we drop the int, which doesn't do anything, and we load the pointer at offset 8. We load the reference count from that, we subtract 1, and then we store that in memory again. Perfect. So, how do we waffle? We basically want to check, is that 0? If so, then we want to free that value. I think the only control flow that we have is a switch. But that is fine. Yeah, that is fine. So we need to switch on something. There was this one to do here. Yeah, we also want to do something else. We want to switch on what? Well, on the result of comparing. Oh, it even compares 0. That is amazing. We don't even need to, create the 0 and then do stuff. We can just do compare 0. Oh, amazing, amazing. With the new value, basically. Yeah, so I don't want to load the value, store that back into the memory, then load that value again. Instead, I mean, it shouldn't be too bad, it shouldn't, like, that memory is in cache, this isn't really slow, but it is simpler to just store keep another version of the value on the stack. New ref count will be a local variable of this. Yeah, of waffle sub from that thingy and 1. And then we store to that pointer the new ref count. And then we switch on the new ref count. And compare 0 had like a really, really weird return thing. I don't know where that is. Hang on, waffle compare 0. Yeah, tag for enum. Yeah, exactly. If it's equal, then it's 0. Compare 0. Okay. If the reference count is 0, then this will be 0. This will put the byte 0 on the stack. Otherwise 1 or 2. Okay. Okay. Waffle switch. So this needs a slice probably of bodies. Yeah. So this will have 3 bodies. Sure. How do we create bodies? Oh, like this. Actually, I think I'll create these waffle bodies by hand in this case, because they are like really simple. They are just a single expression. And they don't have any locals. So the locals will be an empty slice of waffle IDs. And this will just call, so waffle call, the free function. which we still need to create, /compile, do something about that. Yeah, this, right, these should be equal signs, similar to here. We don't need this builder, we'll just do this. And these right here, they just do nothing, so waffle padding 0. Okay, we compare the value to 0. If it's equal, we call the free function, and otherwise we don't do anything. And the free function will be similar to this one. Well, it won't be similar to this one, but it will be, you know, a similar kind of, it will be a call at least. And the free function depends on the type. So compile free fun of the payload type. Yes. And compile free fun of the payload type will generate a function that accepts a pointer to that type and frees that pointer. Yeah, we still need to create that. And again, it will be pretty similar to this one, I think. Dang. It's quite a bit of code after all. I think because that's because the abstraction level is so big. You know, we do both dupe and drop, like generate dupe and drop functions, but we also directly deal with memory layouts and so on. Adding another compiler stage between the putting in the waffle might, you know, basically split up this bigger compiler stage into some smaller ones. Yeah, so we compile the free fun, and rather than doing this, you know, getting something with the payload size, we know that this really is just a pointer. So we get the ref count. Oh yeah, the pointer, we have that already here. Pointer. We just return the pointer. Okay. You know what? I'm gonna put myself up there because these fixed headers, they kind of take away the space. I think if I'm in the top right, then it's more likely that you'll see the good parts of the code, the important parts. Okay, this call doesn't work because it is a slice of nothing. Slice of nothing. What? Well, no, not really. Let's just compile this and see where this fails. Oh. Okay, so it does compile, but of course it's not really good because this free thingy should really not have the signature drop. It should have the signature free. We lay out stuff. We have a fun builder that takes a pointer. We have a fun builder. This takes a pointer. I'm gonna call this. Oh, yeah, param is actually fine. Yeah. So what we do is we extend the type. Okay, for the primitive we don't need to do anything. For never we don't need to do anything. For struct, if this is a struct, a pointer to a struct, and this pointer is freed, the memory there is freed, then the struct itself should be dropped. And if the struct contains other pointers, then those should be dropped, aka the reference count of the object that they point to should be decreased. So, how do we do that? It's so nice and sunny today. Amazing. Let's see. We basically want to load that struct. Yeah. So this is the layout dot. Now we memory layout that type. Yeah, we want to load that waffle load from that pointer, and layout dot size, layout dot alignment. Boom. Yeah, for struct we want to call waffle, yeah, this right here, waffle call. Yeah, you know, do this basically. Oh, it doesn't even depend on the type. Freeing a thing is always just, you know, dropping that value. Amazing. Oh, okay. Yeah, let's put the waffle load in here. Oh, damn. Okay, so we load that thing, and the size will be size, well, 8 plus size, because we also have the reference count in there. And yeah, the alignment will always be 8. Easy. And oh no, hang on. Not really. We have this pointer to the actual value. We want to not load that pointer directly, but we want to add 8 to that pointer. Then load the value from there. Yeah. And then call, please drop that value. And then we want to actually free the allocation. So then we want to do, you know, bodybuilder dot waffle free the param. And we don't, yeah, something like that. No special handling needed here. That's just that. Okay. So then this returns waffle padding. We can also return waffle free directly, because why not? Yeah, this is pretty concise at least. Okay. Yeah. Why doesn't this work? To waffle. I'm just gonna ignore that. Okay. So let's look at the dropping of a linked list. Dropping a linked list means if we switch on the enum, if it's empty we do nothing, if it's more then we drop the int, we decrement the reference count. We load the reference count. We subtract 1. That is the new reference count. We store that into the memory. And we compare that reference count to 0. If it is 0, then we free that linked list node, passing the pointer to it. Okay. Amazing. And yeah, free is defined somewhere here. Yeah, and this just drops the item. Yeah, and then freeze that. Freeze the allocation here. That is amazing. Yeah. Yeah. Amazing. I also have a look at the waffle loads, because some of these should add a pointer to to compensate for the reference count that is inserted there. Okay, so here we have, I'll just go through the loads to make sure that this is handled correctly everywhere. This is compiling a dupe fun. Okay, yeah, here we load the reference count and increment that, sure. For duping, is this? Oh, this is dropping. Okay, yeah, we load the reference count, subtract 1, makes sense. This one for freeing, we add 8, and then load the value that is stored there and call the drop function with that, makes sense. This one may be wrong. Let's see, to waffle. Okay, so this is a switch. We switch on some value, and for the payloads, if there is the payload here, then, oh yeah, we get that data from the heap. But really we need to add 8 to this. So waffle add this waffle word 8 and load that. Okay. And for the closure, pretty similar, I think. Closure pointer will be a lambda has a closure pointer and a function pointer. Yeah, and the closure pointer will be what would that be? Yeah, the closure also has a reference count. Yeah, and then we load that and so on. So we also need to add 8 to this. Amazing, amazing. Yeah, let's make sure when we create a lambda that we also like handling lambdas is something that is not really well done right now. Okay, we also when creating a closure we also add the reference count in there, so that makes sense. What else? I think next we want to handle closures. There were some to-dos in here where that wasn't really the case. Oh yeah, handling closures and dealing with this, you know. Actually, I think the way to go about that would be to not have comp time stuff in the pudding. Yeah, we don't want yogurt values stored directly in here. That made sense in the yogurt, because in the yogurt, you know, comp time values are special cased, and calling a function with comp time values is different than others. Sorry about that. At some point, though, we need to create those comp time values as well. So I think this makes sense. Just store these directly in here, and yeah. Okay. Yeah, that kind of means that we don't have this, but instead we do. Oh, hang on. You know what? Before we do that, this compiles, right? It does compile. Okay, let's commit this. So we added the pudding and all that stuff. Okay. Yeah, we moved that up there, sure. Some things got renamed. Yeah, yogurt pudding is new, very true. We added free things. Amazing. Add pudding between yogurt and waffle. Yeah. And now I can remove these. Handle that down here. And instead we handle ints and strings. With quotes around them. What else? Types. Okay. Yeah, when converting the yogurt pudding, we need to do that as well. Oh damn, what is all this? Yeah, types are not mapped. Expressions. Yeah, there is no pudding aggregate or something like that. The pudding doesn't have memory layouting stuff built in. So let's just remove all of this legacy stuff. Look at how small this file is. Pretty amazing. So, yeah. Converting a value needs to call itself recursively. So let's have this. We're converting a yogurt value to a pudding expression. We'll just switch on the value. Kind. Yogurt value has a kind. Yogurt value kind, which is one of these, of course. Yeah, if it's an int, then we'll just create a pudding expression. pushing op.int of that int and the type plum type.int. Was that correct? I think that's correct. Yeah, if it's a string, then it's putting op.string of that string plum type.string. If it is a struct, this is actually pretty cool. We do something very similar to what we do with runtime known structs. We just create, we create the fields. Which will be a map from string to pudding ID, and for every field in the struct, we don't get the ID because the field hasn't been compiled yet. But instead we push the field. So what we do is we push, field dot value dot to pudding. That is an expression, and when we push that to the body builder, we then get an ID. Yeah. Oh yeah, this is interesting. So for when turning a body into pudding, we go over the yogurt params and expressions, compile them, and then only for the yogurt params and expressions we implement drop operations, which means for these comp time values we don't actually need the dupe call, because they won't be dropped at the end of the scope. So this is perfect. The reference count, when you create something, the reference count is 1. And that struct that we create kind of takes ownership of the value that we've compiled. Yeah. And then this is the value type, I think. For, that was structs, then variance value that probably has a symbol and and payloads. So we'll do something quite similar to this, except we'll call this payloads. And in here this will be payload, variant payloads we push the payload converted to pudding, and then payloads.put, this will be a list of pudding IDs, and here we just push that ID, and here we create a variant which will be pudding variant, where the symbol is the variant symbol, and the payloads are our payloads converted to a slice. Oh man, okay. Yeah, let's break that like this. Okay, for lambdas, what do we do? How do we deal with lambdas here? Whatever we do, we'll do something very similar. We'll do the captures, which will be a list of IDs, and then for each of the captured variables, rather than getting that and duping that, we'll just compile that. So what we do is ID is capture, which will be a value, dot to pudding, returning us an expression, so we need to push that. Bodybuilder dot push that. That gives us an ID, and then we push that ID. Okay. Putting signature, is that not like a function for that? Would have assumed. Or like even better, lambda function. Yep. Oh, the type is interesting. I don't know how the we don't have types in here. So we kind of need to think about how do we represent types. I would just say, I mean, you can't do anything with types, I think. Oh, hang on, there is a putting type. Yeah, there was putting up dot type. Okay, never mind. Plum type dot type. Okay. Amazing. Amazing. Okay. Yeah, I think this is fine. Plum type.int is not a, oh, it's a primitive, and but there is like a plum type int, isn't there? Oh, it's just type. Sure. Then this will be type in not caps. Yeah, okay. Yeah, comp time doesn't exist because yogurt to pudding. Oh yeah. Here instead we do value to pudding. Yeah, right, it needs other stuff. It needs, you know, the function, the fun builder, the body builder, the yogurt ID to pudding ID, the yogurt stuff like that. Although actually, hang on, it doesn't really need them. And putting body builder, does that have a reference to the function builder? Yeah, it does. Okay, so when we, like, the function builder is never used. This mapping is never used because comp time values don't reference any IDs and they don't introduce any, well, they introduce new IDs, but they are not, those newly introduced IDs don't stem from yogurt IDs, so there is no mapping to insert here. Plus, they also don't depend, they don't need to inspect the yogurt. And the fun isn't actually used as well. We just use the body builder. Pushing IDs there as necessary. So yeah, to pudding with the body builder. Same here. Same here. And here. Oh, no, that's the signature. Yeah. Okay, so this just expects the body builder. So much cleaner. And I think that's like some other functions take unnecessary parameters as well. This call doesn't work. Yogurt signature. To pudding of a yogurt signature. Well, that is unfortunate. Let's fix that. To pudding of a yogurt signature will result in a pudding signature by creating a pudding signature with the yogurt signatures string. We're just hold still for some reason. Gotta fix that. Right. Okay. Yeah, to pudding of a yogurt value. 939 expression.type doesn't really exist, but we do have value.type, so yeah. Okay, pudding to waffle. This becomes easier now because this isn't needed. We never have values that are kind of somehow special cased. Values will just be a comp time struct, will just be a pudding struct. That will be the code for creating a struct. Makes sense? Okay, so in here we also never need to hang on, drop fun, other stuff. Yeah, and here, yeah, comp time doesn't exist. We don't need that to exist. Okay, hang on. And the waffle to, no, and the yogurt to waffle thing. Some of these actually make sense. Like we need to int string and type, I think. These are the ones that we've added. Yeah, int string and type. Ints will just result in a waffle word. Strings will result in an aggregate that contains a pointer. Yeah, a pointer and the length of the string. And types just compile to a type. Yeah. Well, you know, types will crash, but that's fine. Okay, that is something. That is nice. Built-in sub-ints, main compare ints. This is our nice dropping of this. Okay. So I think that's the one part I wanted to do. You know, remove, you know, kind of this yogurt value reliance. Yeah, remove pudding to waffle, we remove a lot of stuff. Yogurt to pudding, we remove a lot of stuff. And in the pudding itself. Oh yeah, that makes sense. The pudding and then the stuff that compiles to the pudding and the stuff that compiles from the pudding. They need to change. So remove compile comp time values for normal pudding ops to other pudding ops. Yeah, something like that. Okay, then compiling lambdas. There was some to-dos in here. To-do, yeah, these. Lambda and type. Oh, hang on, we're in the yogurt to waffle. And the pudding to waffle, I think. Here with some, yeah, drop lambda. And dupe lambda. Okay. Yeah. Okay, so a lambda has a pointer to the closure, one part, and it has a function pointer. The compiled bytecode that the function pointer points into, that is never freed currently, and that is fine, I think. Like, actually, at some point we may want to allow freeing that as well, but that's going to be more involved. So functions themselves, we'll just treat them as being, just being there. We don't need to free them. The difference is the closure. We want to reference count the closure. So first of all, when creating a closure, we have to push a reference count as well, and we do that. Okay. So when creating a closure, we also create a reference count that is initially 1. Makes sense. Now, when I'm duping a lambda, what we want to do is just duplicate the closure pointer. We have the closure pointer, that is the waffle member of our lambda, no, of our expression, I think, or param, I think it's param, yeah, of our param, and their waffle member takes an offset and then size and alignment. Yeah, at offset 0 in our lambda, there is the pointer to the closure. Oh, yeah, I think this doesn't make any sense. Okay, and then we load that. From that closure pointer, we load 1 byte, the reference count, and increment that, and then store that back into the closure. That makes sense. Yeah, and this is bodybuilding. Cool, cool, cool. Next, what's next? I think next we want to drop lambdas. So when dropping a lambda, we'll again do something very similar to what we do for boxed enum values. We load the pointer, which we'll call closure pointer. By accessing the param at offset 0. That's the pointer. The new ref count will be the result of subtracting 1 from that pointer. Then we'll store the new ref count into the closure. We will switch on the new ref count, and if that is 0, well, this is kind of difficult. Because at this point, we know, like, the only thing we know is that this is a lambda of a certain type. Let's say a lambda from int to int. And the lambda contains a closure, and it contains a function pointer. And when calling that lambda, we just call the function pointer, giving the closure as an extra, the closure pointer as an extra parameter. So we don't need to know anything about what's inside the closure. However, when freeing the lambda, we can say, well, the closure pointer points somewhere in memory, we'll just decrement what's there, that's the reference count. But if that reaches 0, we need to free that. we need to free the entire closure, and the closure may be different depending on, you know, on the closure. Just because we know this is a closure from int to int doesn't tell us any, this is a lambda from int to int, that doesn't tell us anything about the values that are stored in the closure. There may be a function that is like a pure function, you know, just always calculates the input times 2, I don't know. So the closure would just be the reference count and no actual captured variables. In another place in the code, you may have a closure that like also maps int to int, but it takes the input and then, I don't know, looks up an item in a linked list of ints and returns that. Still a function from int to int. But this function captures a linked list. And if that's the only place where that linked list is referenced, when that lambda goes out of scope, then the linked list should also be freed. So just based on the type here, on the lambda type of, you know, this is a closure from int to int, we can't even, we can't know what's in the closure. Meaning, this is also called type erasure. You know, we intentionally lose information about types. We only know this is a lambda from int to int, and we don't know nothing about the things it captures, even though that that influences the memory layout and, you know, the dependencies and stuff like that. So what we need to do here is find a general way of freeing a closure, and that's not, we can't currently do that. There is no way to do that because we can't kind of get information about the closure just from the lambda type. So I think the actual, we need to actually store another pointer for the lambda. A lambda should consist of a pointer to the closure, a function pointer that is called when you call the lambda, but it should also contain another function pointer to a function that can free the closure. So when a lambda goes out of scope, we can decrement the reference count of the closure. We can do that because the reference count is always stored at the beginning. So we can do that without knowing anything about the type of the closure. But when we see that reaches 0, we don't know anything about the data that is stored in that closure and how to free that. So we just call this free function pointer with the closure pointer. That's the idea. It does mean that every lambda grows from, you know, closure pointer plus function pointer, aka 16 bytes, to closure pointer plus function pointer plus closure freeing function pointer, aka 24 bytes. We could store the closure freeing pointer within the closure itself, actually. Maybe that, I think that makes sense, actually, because you don't, you know, it may be that you store a lot of, or that you have the same, yeah, you, what the closure, what the lambda does is associate the closure type with a function pointer. Then again, I'm going to keep it simple. I'm just going to store the lambda, the closure freeing pointer, whatever, directly in the lambda. Whoa, okay, this is surprisingly complex. Compile drop fun. Dang. So that's, we can't even do that here. I'm gonna leave a to-do in here. That is crazy. That is crazy. Yeah. So compile free fun. We also want some sort of compile closure free fun or something. Damn. Okay. Yeah. I'm not entirely sure what it takes, but basically when creating a lambda, to have a uniform representation consisting of a pointer to the closure, a function pointer to the lambda body for freeing the closure. Yeah. Oh damn. Okay, so we memory layout the closure in here. We build parts. Oh yeah, we build the concrete closure instance. We have a closure pointer. Ah yeah, and then here we have this list of the closure function pointer, the waffle function pointer, but then also another waffle function pointer of some waffle signature of closure, like compile closure free fun of the closure captured types. I think, yeah, captured types is fine. Damn. Oh yeah, this does need the funds. These definitions have the same name, but arguments don't match. Compile closure free fun of plum type and a map waffle signature waffle fun. Yeah, so this compile closure free fun should actually take the types, the captured types. And I think that is fine, because even if you have multiple closures that capture the same types, those types will be layouted in the same way, and freeing those will be the same. That's crazy. So the layout will be, well, the layout will be whatever we do down here. Capture types push, memory layout closure. Yes. Oh yeah, by the way, that should be a list, should be a slice instead of a list, I think. Yeah, this, turn that into a slice, and yeah, layout is captured types, memory layout closure. Amazing. So now we know the kind of closure that we want to free. So yeah, this will be, we want to create a function that accepts a pointer to the closure. Yeah, and we don't have a type in here. So what we do here is we want to free all the captured types. Yeah, which will be, hang on, we want to not free but drop all the captured types, which will be similar to dropping a struct, actually. Something like this. Yeah, for each type in captured types, the capture layout is type memory layout. And then we call compile drop fun with, yeah, for that type with the waffle member that compiles the layout dot offsets or something, closure memory layout, or layout enclosures, capture to offset. Okay, yeah, I guess so. This is that, and in here we have to do type item, and then in here we can say layout capture to offset get type index with the capture layout size and alignment. Okay. Okay, and in the end we just free the closure directly. Perfect. Okay, yeah. Oh yeah, this should convert them into a slice. Assembling binary, egg, boom. Yeah, I think we don't even use closures in our example. Let's change that. Make list. And inc. What does inc do? Oh, it increments the list. Well, I guess. Let's instead map this. Using a function that takes a b, which is an int, and equal sign, hit that, and converts it into b plus c, where c is defined out here. Also, let's say we sum this. Pipe with multiple children. Oh, indeed. More annotation. Please, more. Yeah. Dropping a lambda. Yes. In here, drop lambda. We get the closure pointer. We update the reference count. We switch on the new reference count if that is zero. Then what we do is similar to when we call the closure, we do an indirect call. Let me, oh, hang on, that can't be the only case where we do indirect calls. What if we lambda call? What do we do here? Oh, it's waffle call in, not waffle indirect call. Well, okay. Anyways, yeah. Okay, so this is just waffle. Let's do it like this. Hang on. Waffle call indirect, and instead of knowing the function, knowing the function up front, we'll have to get the function. So we'll have to waffle member the parent at offset 16. That is the pointer to the capture, the pointer to the closure freeing function. Is there still to do down here? Yeah, there is. Let's remove that. Yeah. I think we need to ignore that for this to compile. Offset too big. That's interesting. If that's like a 3 million something, then I know, okay, you know. Oh, 16. Oh, that is actually... Oh, I see. So waffle member, hang on. Member. Oh, right. When we create a closure, right here, oh no, we create these function pointers. This should be 16 bytes. Sorry, this should be 24 bytes. I don't know why that doesn't work out. Oh, I see. In memory layout, I think memory layout closure. Yeah, sure. We have this generic memory layout function. Not anymore, not anymore. Amazing. So we have aggregates. Yeah, sure. Yeah, layouting arbitrary types. That's it. Yeah, in here, this is 24. I don't know what to do about that. But sure. Bytecode. Hang on, this is the waffle or something? No,
know, the pudding. Oh no, the waffle. Yeah, makes sense. Let's look for some closure stuff. Yeah, here we have a lambda. But that's just doing the body. Yeah, this doesn't do anything with lambdas. Map takes a lambda. Indeed. So it duplicates this list, switches on the tag. If that is a thing, then it creates an empty part and dupes that and drops that original one and drops that and returns that. And in the case of 1, what we do is we dupe the lambda, which is 24 bytes, correct? We dupe the int, we call that lambda offset 8 with the int. Oh, hang on. No, yeah, here with the int and the closure. We do other stuff. We load. Okay, yeah. We add 8 to that pointer, load 70 bytes there. We do that. We cast stuff. Okay, sure. How does the I want to look at some of the lambda dupe, drop, and free code. Here, dropping is nice. Dropping a lambda. What it does is the lambda is 24 bytes. The first at offset 0, it contains the closure pointer. Okay, we load those 8 bytes there, that word. That is the reference count. We subtract 1. That is the new reference count. We store that into memory, and then we switch on that. If it is 0, if it is equal to 0, then we call that closure free thing stored at offset 16 with the original, with a closure pointer. Makes sense. And in reality, that will be this function, which then takes the closure pointer, just drops the int. Oh no. It should drop the. It has to free this. Yeah. This has to be +8. This is free. Yeah, compile closure. Thank you. Free fun. Yeah, this offset. We want to drop something. Yeah. Oh, but the param is a pointer. I see. So we need to dereference the closure first. That is a waffle load of waffle add of the param
and 8, and we add the layout, size and alignment. Okay. Then we have the closure. And then for each of the captured types, we get the member from the closure. Yeah, that's more like it. Okay, it is a different number. I don't know if that's good or bad. But let's just look at the closure freeing function. Yeah, okay, so we could, let's put that into a local variable, so we don't reload that for every single captured thing. Yeah, so this will be body builder dot push dot local of the waffle load. Man, my voice is really not used to talking so long. Okay, yeah, please, it says please free the closure that captures an integer. And we're like, okay, sure. This is the pointer to the closure. The pointer at the closure also contains the reference count, so we add 8. We load those 8 bytes there, the int. Then we drop the int. And we free the original pointer. That seems correct. So freeing the closure, perfect. Next, dropping and dropping, I looked at that before. Which is just subtracting 1 from the reference count, storing that back, and making an indirect call to that freeing function. I want to look at dupe for the closure. Yeah, there is no way to, oh, here. Okay, yeah, we just load the reference count, add 1, and store that. Perfect. That's all I want. And then the main function, where we create the closure. That's the last piece of the puzzle. This is sum, okay. This is the main function. Oh damn. Oh man, okay, so at some point we call map, using 11 as the closure. 11 is up here. Hang on. Oh yeah, these get reordered. We call map with this enum and the closure has a nice round size, 24 bytes. So we pass that first, then no padding, and then this one with an odd size. So 13 is the closure, 24 bytes, perfect. Result of casting this, yeah, that's an identity function, sure. Yeah. Still, I might want to look at that too. Sure, here's dupe of that. Amazing, of 9. 9 is here. 24 bytes. Oh, look at that. This is pretty great. This is the closure body, which, this is the closure, which we allocated here. And then we stored there this right here. Oh no, we allocate only 8 bytes and then we store 16 bytes in there. That's not good. That is not good at all. We store there the reference count for the closure, which is 1, and we store the actual closure data, which is the C variable that comes from the outer scope. Okay, so allocating the closure does not work correctly. Allocating the closure for the lambda. Because here we allocate, oh yeah, the closure size, but really we want 8 plus the closure size, so that we can then store the closure pointer and other stuff. Let's check the same thing for linked lists as well. I'm not sure that we did the correct thing there. Okay, yeah, also some index out of bounds. Shit, okay. Yeah, so we allocate 16 bytes. And then we store there in this 8-byte pointer. And where that points to, we store this 8 bytes for the reference count and then 8 bytes for the actual int. Okay, this is correct. Like, this creates a correct closure. And then we create a lambda with that closure pointer, pointer to the lambda function, pointer to the free function for the closure. So far, so good. Now let's, like, I think closures should work, but maybe recursive types don't quite work yet. So let's look at make list and make sure that it allocates enough memory, because I'm not entirely sure about that. Make list. Yeah, so it does something. Yeah, this is the empty case. This is the non-empty case. Oh yeah, this is true and false. We check if this is 0. If it's true and false. Yeah, false comes before true, so we do this. If it's not 0. And here we... At some point we should allocate memory. I'm not sure where though. Oh, it's within the cast. Right. Let's look at the cast for the recursive type and at the cast for closures. And otherwise I have no idea where, like, why our code fails. Cast. Okay, so this is the one cast I want to look at. The cast from closure to closure, where we literally just copy that. So we dupe that and we drop that. Sure. And return that. Yeah, that seems correct. And then cast from... Yeah, this doesn't really do anything. I'm looking at cast for the cast that casts a maybe thing to a more thing to an empty or more thing. Hang on. Oh no, looking for this cast actually. Yeah, if it's empty, we do something. If it's more, then we do this. Is this correct? Yeah, I think so. I think so. We store in here 8 bytes. And then expression number 8, which is 17 bytes. Yeah, total of 25. We allocate enough memory for that. Okay, I have no idea where that stuff is failing. That is kind of unfortunate. Let me take a break and yeah, I'll see what I'll do after that. I got kind of stuck because I didn't know how to debug stuff. So yesterday I thought, like, maybe just, as an exploration, I'm gonna write another compiler stage. And this is what I did. I didn't record that. I was like, I'm not even gonna bother recording this. It's just like a exploratory thing. But turns out it's pretty useful and it works. And I don't know what the bug was, but it now doesn't exist anymore. So yeah, why yet another compiler stage? I mean, in this video alone, I added 2 compiler stages. That's kind of crazy. But it makes sense, believe me. The thing is, this back end of the compiler really does have to do a lot of work. It has to memory layout types. It has to desugar lambdas into closures and function pointers and so on. It has to memory layouts. I already had that. It has to insert like reference counting stuff, dupes and drops and so on. And tackling all of that at once was impossible. Converting yogurt to waffle directly, including reference counting, I attempted that at first, but it didn't work out. So naturally, I introduced another compiler stage, the pudding, where we do the reference counting from converting yogurt to pudding. And then in the pudding, we already have these reference counting instructions, dupe and drop. But turns out converting pudding to the low-level waffle memory stuff is still a huge gap, because in there we do not just the memory layouting, but also this desugaring of lambdas, which is quite complicated, especially compared with reference counting, because now you need to add ways to duplicate a lambda, for example, meaning to increment the reference count of the closure, and we need to store a function pointer to a function for freeing the closure, and it got really complicated. So I basically split this compiler stage into 2 parts again. So now we go from yogurt, the representation with types, purely the highest level semantic representation of our program. We insert dupe and drop operations for all values, irrespective of whether they will be actual like heap allocated values or they are just an int or something. And most of these reference counts, will be no ops, because inline values that are stored inline, they don't have a reference count, but only allocations have reference counts. But still, it's useful to have these dupe and drop operations in there and kind of be able to reason about them on a semantic level. Then that pudding is turned into Pesto, which stands for, let me look that up, hang on, pointers, enums, structures, and tamed operations, because the operations are not as wild anymore. We don't have lambdas or lambda calls or something. Yeah. So this is kind of like a representation with C-like types. Back when we compiled our program to, let me move myself here, when we compiled Plum to C code, we also compiled that into structs and enums. Well, not enums, but unions, and pointers in between them. And we didn't have to think about the concrete memory layout, in which order do we put bytes in memory, where do we allocate memory, all of that disappeared. We didn't have to, the C compiler took care of that. And now we have this representation with C-like types. And it's a bit easier to reason about that and even read the intermediate representation and thereby maintain this and fix bugs and so on. So let's maybe look at let's maybe look at the representation and then look at some at the length of the source code, how that kind of played out. Let me go to the main file and kind of enable debugging. So I have an example program here that is very simple. Main. You can see that it creates a variable c, then it creates a lambda that that takes an int and adds c to that int, c coming from the outer scope, so it captures something. And then in here we call that lambda with our input. So let's compile this and see what the result is. Turns out the result of this should be, I think the default input for main is 3333333, a lot of threes in hexadecimal. So adding 1 to that is 3333334. And now let's enable some of the intermediate stages to see what's happening. First of all, let's start with the yogurt. Oh, please work. I'm actually not sure that the printing is up to date. If this works. I hope it does. Yeah, it does. Okay. Okay, so the yogurt is reasonably small, I would say. Here we have the main function. But let's start with the plus function, maybe. You know, adding, like with this function. This is the built-in add-ins function that the compiler automatically creates in the built-ins module. It takes two integers, adds them. Here's a function for casting an integer to an integer. Like, that doesn't really do anything, it just returns the input to this function. But still, it exists. Then adding two integers. This is the plus function defined in the standard library. It casts the first argument to an integer, which essentially does nothing. It casts the second argument to an integer, and then it calls this built-in add-ins function with those two cast integers, and it returns the result. And then the main function takes a comp time 1, which is an integer. It creates a lambda, and this is a lambda that captures this 1 from the outer scope. And the code for that lambda is this one, and that's defined up here. Yeah, so this is a lambda, which we can see because it captures something. So it doesn't just have these explicit arguments, it also can have multiple of these arguments that are implicitly provided. And we can see that it, again, just casts the integers and adds, it calls the plus function. And then finally, after we created the lambda, we call that lambda here with the, oh yeah, this is an indirect call. You can see these calls here, they are static. They have this kind of string of which function they call. This call doesn't. This just has an ID, which is a lambda, and that lambda is called with this input as the explicit argument. Implicitly, it also captures this one. Okay, so this is a representation of the code that really is purely on the semantic level. Like this, you can read this code and it corresponds to the source code pretty much exactly. And now let's go through the compilation pipeline and see how that changes. So first, that yogurt is converted into pudding. Pudding being the program using dupe and drop instructions to neutralize garbage. So we add reference counting stuff in here. Yeah. Boom. Yeah, so there's a lot more stuff going on here. Again, this is not optimal. Like, I'm just focused on getting this to work at all. I'll do optimization passes where you're casting integers to integers. We can just remove that. But for now, I'm just trying to get things to work at all. So within each of these functions, we now duplicate values before we use them. Okay, we kind of increment the reference count, or we do that. Yeah. So in here, when we call, previously we would just call the casting function, cast int to int with 0. But now before we do that, we also dupe 0. So we increment the reference count of that. Because this casting function is responsible for dropping the input when it's no longer needed. And we do that same with this one. Here we call a function with 2 arguments, so we dupe both of them before calling the function. And then finally, we dupe the thing that we want to return in the end. And then we drop all like intermediate expressions that were defined in the scope, because all these variables go out of scope. So if they allocated something, that memory should be freed. And at the end, only this, this thing that was duped in extra time, this is what remains. Because this basically increments the assume the reference count of this is 1, which it probably is. This would make the reference count 2, and then down here it would be dropped. But unlike these, the reference count doesn't reach 0, but it reaches 1, and then that is returned. Yeah, so a lot of dupe and drop stuff in all the representations. And we can see that even for the lambda, if that captures something, that also means that this surrounding variable is duped before that. This is still, these dupe and drop operations, they work on any value, whether that's an int, a lambda, an enum, something. It doesn't matter whether there's heap allocations happening or not. So this is purely semantic stuff. Now the Pesto. Disable the printing here, enable the printing here. In the Pesto, we think about not concrete memory layouts, but we think of how can we represent types as structs and enums and pointers. So for example, if we have a recursive enum, we have to put pointers in there somewhere, because you can't have infinitely big types. That would be explicit in the Pesto. And lambdas, in particular, they are also really desugared into function pointers and closures and so on. And we can see that. Hang on. First of all, let me show you not the entire Pesto, but at least Pesto types. Yeah. You can see, rather than having lambdas and structs and whatnot, we just have ints, pointers, structs, and enums. And enums, they don't even have like a slice of payloads. They don't, like the enum variants, they don't have multiple payloads. They just have a single payload here. And when calling a function, we also just provide a single expression as the argument. Well, except for the built-in call instructions. So wherever possible, we if we want to pass multiple values at some point, if we want to store multiple values, we also just wrap that in a struct so that we just pass around these singular contained values. And you can see that in here. The main function accepts this one value that represents all arguments. And that's a struct that contains fields that are named after numbers. The first, at 0.0 is the first argument for the function. .1 would be the second. There is no .1, but you get the point. So the main function accepts an int, which means that this is how we get the first argument. Here we create a comp time known integer. We call a dupe of int with that integer, which doesn't do anything. You can see that I can look for the dupe function soon, but it's very similar to the drop function. It just returns nothing. Nothing being an empty struct, like a struct with no fields. Yeah, the dupe function is down here. Yeah, exactly the same. And the interesting part now is lambdas. Because rather than having lambdas and capturing, having this capturing as an explicit thing in this compiler stage, this is desugared into this sort of struct. Every lambda becomes a struct with a function pointer that represents the lambda body, a function pointer for freeing the closure, and a pointer to the closure itself. And here we want to create that lambda. This is the call. This is the code for creating the lambda, which basically creates this closure of all captured variables, aka the one that we've created here. And this is just a struct with a field named 0 with that one, because the closure can capture multiple variables. It captures a slice of values here. So yeah. Right, we have this struct. Then this right here allocates memory for that struct and returns a pointer. And every pointer implicitly has a reference count. So now we've changed reference counting from working on values like this dupe and drop stuff that works on every value, that only works on pointers now. And every memory allocation implicitly has a reference count that is mutable. The value itself here is not, you can't change that once you've created that on the heap. yeah, we also store a pointer to the function, to the lambda, and to the free function. And yeah, this right here creates the closure, creates the lambda containing a function pointer to the body, function pointer for freeing the closure, and the pointer to the closure that we've allocated here. Yeah, and then calling that lambda means we duplicate the lambda, we duplicate the explicit argument that we pass into the lambda. And then here's the indirect call. So what we do is we get the closure pointer from that lambda. We get the function body, function pointer to the lambda body. And then we implicitly call that with a struct that contains all the arguments, like the one, like our argument that we pass into the closure, that we pass into the lambda, and the closure pointer. So irrespective of which closure we have, if we have a closure that maps int to int, this is always the type that it expects. It expects the arguments, like argument 0 should be an integer, and it expects a closure pointer. And the other arguments would be put in here as well. And then inside the lambda, what we do is we take from this argument struct thingy, we take the actual argument, we take the closure, we load this closure, and we can do this because we know what kind of type of closure we expected here. We know what is in memory there. It's just an integer. And yeah, then we extract the actual integer from that, which is field 0. And then we do the actual closure stuff, which is not as interesting. Interesting is when dropping the closure, we get the function pointer. Again, every pointer is reference counted. So this drops, this decrement is the reference count of that pointer, returning the new reference count. We compare that with 0 created here, and we switch on the result. It can't, this can't really be, it can't be less than 0. It can be greater than 0. The only thing we worry about is if the reference count is equal to 0, then we need to free the closure. And because this is any lambda, we don't know what kind of stuff is allocated within the closure, we take the free function pointer from the lambda and make an indirect call for that. Damn. This is crazy. And this is the actual code that gets called in that case. Takes the closure pointer, loads that closure pointer, drops the end, frees the closure. Yeah. This is crazy. The fact that things work at all is pretty nice. And this is way more readable than the next compiler stage, the waffle, which was, initially I looked at how can I compile these dupe and drop operations and so on into waffle operations. It turns out that is really difficult. Having this sort of readable representation where we still have structs and we can say dot closure or dot free or something, that is super valuable. Yeah, and the waffle didn't really change, except that I added a free instruction. Let's see. Yeah, I added some assertions, I refined them, okay. Oh, there was already a free instruction. Well, okay, it wasn't really used, apparently. So that kind of leaves me to what do I do now? I want to clean up this code, because a lot of this is organically grown code, and there is a lot of refactoring and cleanup that needs to happen. But before I do that, let's just quickly look at the code size, because I think that might be interesting. We had this waffle to bytecode, which was 300 lines of code. Oh, we still have that. But we had this other thing, yogurt to, where's that down here? Yogurt to waffle. Yeah, converting our high-level yogurt representation directly into waffle. That was like 330 lines, like pretty concise actually, but it didn't do any sort of reference counting. And reference counting at this compiler state would have been super difficult. Like we would have to insert dupe and drop, like insert all the code for handling reference counts. But we also want to optimize that code. We might want to reshuffle dupes and drops later on or eliminate some of them. And like doing that ad hoc while we are compiling code is really difficult. Having an explicit intermediate representation for that makes sense. So the pudding was born. Pudding being here. And then we have this yogurt to pudding, which is, well, just inserting dupe and drop instructions. It's like 200 lines. This is not optimized yet. Like we insert them at every possible, that's a very naive approach. So this, the size of this file will grow once we get cleverer about where we want to introduce them. But still, this is nice basis, to have this nice compact strategy, and we can iterate on that later, make that better. And the pudding to waffle that we had, this was the one that had all the complications in here. This is like a 600 line file, yeah, and it wasn't even correct. Like, this is where bugs came in, and there was a lot of ad hoc fixing of stuff. For example, when we create an enum or something, variant here, yeah, we would have to take care, well, is this a payload, is this a pointer? Depending on that, we do different stuff. We allocate memory for that, which is a word with 8 bytes for the reference count plus the payload size. And then in that we store the reference count, which is 1 in that case. All of this, like this intermingles this layouting of like where do things actually live in memory with the decision of, do we use pointers for payloads or not? Where do we use padding? And that again with the decision of, now we also add reference counting to the mix and have these constants like 1 in here and adding 8 to things. And when getting an enum member, like loading something, we would have to add 8 to that offset or something like that. Oh yeah, here, this is cursed, We have a switch and we see, oh, this is a boxed thing, so we get a point. We know that this just stores a pointer of size 8, and then we add 8 to that because we want to skip the reference count, and then we load that thing from memory. Like, this is very complicated logic, very complicated, and 600 lines of that with bugs inside is a mess. So now that got simpler. Instead of lowering pudding to waffle, we now do pudding to pesto, which is here, which granted is complicated. Like, it is still, almost 600 lines, a bit shorter. But we don't lower to memory directly. We don't do memory layouting in here. We don't decide where things live exactly. Instead, for example, for function calls, the parameters, they get put into a struct. So in here, for example, we just create a struct with these types, and these types, they are just a string of the index. So the struct has fields 0, 1, 2, and so on that contain the actual struct values, and then maybe also a closure pointer. So this is comparatively simple, explicit code, at least compared to what it was before. So everything in here acts on this kind of value level, we don't have weird offsets like +8 or something. We don't have, adding weird ad hoc things. The only thing is, let's maybe comment that out. I'll just remove that. The only thing is that yeah, we do have special casing of handling pointers in enums, but yeah, like here for example, when creating an enum thing, we just say, either we just put that value in there directly, or we get that value and then put that on the heap with this pesto new thing. So this is a pointer. But again, this is, the complexity of this is so much more explicit and so much more simple than this part. Where we decide, let's malloc the payload size +8 and then store in that pointer a 1 followed by the actual payload. Like this sort of stuff is got much simpler. And then only in the next stage, the pesto to waffle, which is here, we did that actual the actual memory layouting and so on. And actually this file contains the memory layouting logic directly in here. It contains the logic for layouting, getting the size and alignment of any type of layouting structs and layouting enums. And that's it. Compare that to the previous memory layouting where just the memory layouting, not some compiler stage mapping, was 400 lines. Because I tried to reuse the memory layouting for function parameters, for enum payloads, for structs, this reshuffling of fields to make things efficient. And we don't need that if we wrap everything in structs before. So that disappeared. Here we had this separate aggregate layout thingy, which did the actual layouting logic. And then we had layouting function parameters, layouting closures, layouting structs, layouting enums. Well, yeah, we still have that. But again, still, even enums are simplified now because we don't have multiple payloads. So all of this memory layouting got like 400 lines. And here's like 220 lines, half the size. So I put it in the same file as the actual, mapping the compiler stages, which is just, let's see, 220 to 390, okay, like 175 lines or something. So I think this really was worth it, separating these stages out. Just because, maybe the overall line count increased, granted, but the individual complexity peaks there, they got so much lower. All right, now let's remove these files that we no longer need, like this one, like the memory layouting, like the putting to waffle. Yeah, there's an error here. Multiple type definitions. I don't think so. Nope, that compiles. Okay. Yeah. I think first of all I want to commit that and then work on simplifying that and refactoring stuff. Yeah, memory layouting got removed. Hell yeah. Let's make sure this makes sense. We no longer have yogurt to waffle or pudding to waffle, but instead we have yogurt to pudding. Yeah, which didn't change since the last iteration. We have pudding to pesto, and then we have pesto to waffle. Nice. Yeah, just some small fixes. That's fine. Okay, Yeah, I guess this is Pesto. Another compiler stage. Amazing. Yeah. Whew. Cool. Very cool. Yeah, I've kind of only walked you through the code right now. Not done anything significant. And I think I'm going to leave it at that for now and kind of refactor that and then wrap up this video later on. So, see you then. Alright, let's change, first of all, the signatures. I think signatures are kind of a weird thing. Let's replace them with strings. Yeah, so in the yogurt, yeah, here we have, the yogurt and the functions are mapped from signatures to yogurt funds. Let's just use strings. Let's not overcomplicate things here, right? And yeah, maybe for calls we might need to change that as well. Yeah, we do. Okay. And here yogurt lambda value refers to yogurt signature. No, it does not. And also, like, this has the function at the end captures. Let's do that here. Captures is a weird name. Captured. I should maintain maybe a to-do list of things I want to make consistent. To do captures versus captured. Pointer versus pointer, and we'll see what else we find. Oh yeah, builder is bodybuilder in several places. Word versus int. Yeah, okay. I'll find some more over time, probably. Okay, so we have this. You got a lambda value where the function is just a string. This is all fine. Okay, and then in the place where we convert the egg to waffle, we don't have any. What's going on here? Yogurt stack entry just has that. Yeah, sure. Okay, sure, we have compilers here, but the builders are in the unencoded compile time. Yeah, I see that. Compile takes a yogurt compiler. Yeah, okay. Here is a yogurt signature thing, and I think that makes sense. However, these should just return a string. Yeah, and it doesn't really have, like, this is not yogurt specific. Let's just call this signature. Because, I mean, this accepts yogurt values, so this already won't collide with any other function. And this one is, I think for plum types, we also, signature is, generic signature is a better name for that. Yeah, okay. Yeah, this doesn't exist. All these, they are just signature. Nice. Sure. This is weird. The fact that this is commented out well. I'll get to that at some point. Yeah. Oh, also in lambdas, this is sometimes called function, even though it's a signature. So function versus signature might also be worth looking at. Yeah, where does this arrow out? In egg to yogurt. Well, yeah, obviously. 75, indeed. Signature is just a string. And that makes sense. I mean, that is descriptive enough, I would say. Yeah. Let's see, we have start running, done running is currently running, all with signatures being a string. And then we have start compiling, done compiling is currently compiling. Okay, and here we have define is defined and get, all of which take strings. That is nice. To pudding refers to yogurt's signature. Yeah, true. So this is basically all the yogurt stuff, you know. And then yogurt to pudding. Like, hang on, in general, pudding is the next compiler stage, and it is here. It defines its own signature, if I'm not mistaken. Yeah. Let's also just turn that into a string, you know. Keep things simple. And yeah, like that, this is called index. Hang on, how's that called in the waffle? Int. Yogurt ID. Int versus index. It says expressions, but it's actually a list of IDs which then reference the outer expressions. Should that be IDs? Should that be I think expressions is fine here, because these IDs, they are really just, you know, the ID of an expression. So yeah. Pudding call, so it just has a string in here. Yeah. Pudding type, yeah, that doesn't exist. That's not an accident, that is a design decision. Yeah, this part right here can be removed because we don't have signatures anymore. This no longer matters if value.captures is some captures stuff. Yeah, that is actually useful. think our fun values, they have captured variables. Yeah, they have. Okay, next up. That was simple. Yeah, next up, let's look at the Pesto, where we have signatures here and in here. Here we map a signature to that. Yeah, this is just that, I guess. Simple. For the drop function, similarly simple. For the free function, again, similarly simple. Free, I'm gonna put closure in there as well. Oh yeah, this returns just a string. Okay, yeah, I like that. Nice. Yeah, let's see, is there anything to pudding in yogurt to pudding? Yeah, this doesn't make any sense. To pudding. Hang on. What? To pudding. 6. That. 1/6 something. Oh yeah. And the fun key is automatically a signature. Oh yes. Yeah, this is like the thing. Yeah, it's technically stricter, typed in a more strict way. I get that. But at the same time, like, it doesn't really, like, making accidental errors with the signatures is like very unlikely. These signatures, they are very basic concept. So yeah, we could type out everything, but it also means that the code gets more complex, and now you need to map those signatures, and you need to implement equals for all these signatures and hash and whatever. And just using strings there is so much easier. Like, this is just unnecessary boilerplate. Yeah, then printing these. Nope, doesn't need to be done. Okay. Yeah. Yeah, this right here is just signature dot larger. Boom. Simple. Well. Compile cast fun. Hang on, in extra yogurt. Yeah, this just returns a string. There is no type named yogurt signature. Indeed. And 4, 6, 8 should just be a string. Are there other errors in here? No, not really. Interesting. 506. And then yogurt to pudding. Of a string. And the lambda, we do this, but this is just a signature directly, which we can directly use. That is pretty amazing. Same here. Always readable, you know, and not this accidental complexity everywhere. 119. Yeah, sometimes removing, you know, fancy typing stuff is really the best way. Yeah, Pesto signature does not exist. That is true. This should just be a string. Thing I noticed before, yogurt class net versus, yeah, there's like a stack that I'm gonna work on. Let's see, key to Pesto and pudding to Pesto. 533. No, this is just a string. We can immediately use that. Same here, just put that in there directly. Simple. So simple. Pesto to waffle 288. Yeah, this is just that. Find a pointer of a. And this is just a signature. Even simpler. Even simpler. Oh yeah, this down here. This waffle call just calls the function. Wow. Readable stuff. Crazy. Yeah, waffle. Oh, hang on, we still have a waffle signature? Oh, no. Let's remove that. And then let's use strings in here as well. Yeah, I agree, this is not perfect. Like, this is... even as though it will make sense to make a patch there, you know? Like this is not, the problem here is not that this is, it is not obvious that this is a function signature. The problem is that we nest types so deeply here, when we should just put this in here. Patches is a list of patches. Yeah, this is yeah. Okay. Yeah, this is nice. True, in the waffle signature we probably have some constructor for that, I assume. Oh, hang on. Function pointer also just sets the string. Here we have waffle IDs, waffle signatures. Yeah, these right here, they can just be, all of that goes away. And this is like writing waffle. Okay, yeah. Yeah, the call just accepts a function. Yeah, function pointer as well. I think these are the only two places. Yeah, right. There's no type named waffle signature in to waffle. Pesto to waffle. Indeed, this is just a map from strings to functions. Waffle to bytecode. This is, the code becomes more readable. What? What? That is crazy. Yeah. 202, here we should put a patch. Like that. Of course, I'll just fix on a single line. Two. Every patch. Oh, look at that. We take the where thing, and what we put there is this. This is so much more readable. Okay, yeah. So this is basically replace. Oh, hang on, not the to-do list. Replace signatures with strings. Simple. Then several things in the yogurt I noticed. This, I want this to be an integer. index is the better term for that. Hang on. Okay. Clean up yogurt ID. Let's look at this list. This, then yogurt parse map versus and yogurt. Oh right. So when converting to yogurt, now first of all, I think in the yogurt there should be a way to. Okay, there is a way to construct a yogurt like this. But in act to yogurt, right at the end, we just do. Oh, now I have no idea how this code is organized, apparently. Because I was looking for the main function. Like, you know, the main, like, compile function. What the hell? And map. Oh, no, this seems reasonable actually. And they just pass around this yogurt compiler, which contains the map. Okay, was this not the yogurt? Was it in the pudding? Like in, you know, pudding, you know, something to pudding. Yeah. Oh, yeah. Yeah, exactly. I think here we should just pass in the pudding. Like that. And yeah. Instead of a list of functions. And then we can also directly add those. Like this expects a pudding, but let's say we have a pudding constructor that returns a pudding with funds being an empty map. And then in here you can just say create a new pudding. That is returned in the end. And yeah, here you just pass in a mutable version of pudding. So this to pudding though, it returns a pudding file. Like this could just add itself to the pudding, I think. I mean, this is fine. Yeah. And this right here, I'm just going to write mapping, because it's the mapping in this compiler stage. Nice. Clean up pudding. So what else? Yeah, this is what I did. Yeah, function with signature. I think function is actually fine. Oh yeah. Let's do the pointer thingy first, because I think PTR is a very fine. Like pointer is used in so many places. So if it's not a comment, I think I want to find with PTR for pointer. this is just, yeah, also here, you know, PTR is very fine. In comments, I might use pointer, but in the code, I think PTR is fine. Yeah, this is not really needed, so let's remove that. Yeah, then, oh yeah, this is just a to-do. Here we use PTR. Then let me zoom out so I can change that. Yeah, that's just comment. Oh, hang on, not comment. Nope. Comment, not comment. This reads almost like a comment, but well, I mean, I can just change all of these to that. So there's a comment, this is that, yeah, this is that, okay. Only occurs in comments. Here, store .ptr. Yes, please. Sure. Yeah. Then captures versus captured. I mean, by default I would say captured with a D. And then again, you know, functions, when they are defined, it's more like, you know, this function captures these variables. That makes sense. And the lambda captures variables. Captures is actually fine, I think. Yeah. We're not putting to something, putting to Pesto. Yeah, okay. Putting fun captures stuff. It does read quite naturally, I think. The lambda again captures stuff. Makes sense as far as I can see that. You would fun captures stuff. Yeah, sure. You know, let's stay. Oh, what is this? Interesting. In the syntax highlighting. Okay, yeah, so captures is actually fine. Then builder versus bodybuilder. I think in some places, yeah, so you're going to putting, you know, you can say, hey, I have this fun builder, putting fun builder, I want to build a I want to create a bodybuilder. I think I want to name that just builder. So I have, you know, a fun builder and the builder, because the bodybuilder is way more common. Builder. Oh, yeah, might have changed too much, because I might have changed one of these. Yeah, this is what I'm talking about. you know, just being able to say, well, create a builder. That's cool. Create a builder. Damn, like we create a lot of builders. A lot of builders. Did not expect that. Yeah, in here pesto to waffle. Instead of this, let's just do builder. Amazing. And yeah, in some places that might blow up, but we're gonna fix them now. Yeah. So in yogurt to pudding, we have to do bodybuilder. Okay, that actually worked. What? Sure. Okay. Yeah. Builder. Rename body builder to builder. Finally, word versus int. I think in the waffle, like in the entire compiler, these are called ints. Except in the waffle, where we have words. For no real reason, to be honest. I could also rename this to duck. Well, I think, yeah, it's gonna be int. Boom. Yeah, waffle int will create the given int. Makes sense. Yeah, so using that is something to waffle up here. Yeah, this will be waffle int. Oh yeah, in general waffle word will be waffle int. Cool. Yeah. And waffle to bytecode, we do this. If it's an int, yeah. This is sensible naming, you know, just having 1 and 8 in here. That is unambiguous. I like that. Nice. Yeah. This looks pretty cool. Nice. Yep, rename. Actually, does it say word in here anywhere? As, you know, its entire. Oh yeah, you see, let's rename these places as well. Is not a word, is word, oh. I think I want to rename that actually. Yeah, is. I want to have two things. This pointer and is int. They do the exact same thing, but they are semantically different. So is, you know, for the int operands, we check that these are integers. Should be right. Yeah. I mean, we have the stack trace, so we know that this is. Like, we are looking at int operands. Yeah, where else do we use that compare 0? This doesn't like, you know, it doesn't tell us anything. Is PTR, that is, you know, that makes sense. Yeah, same for load and store. Oh, look at this. Things that are the same but are semantically different. Nice. Okay, so we have npm garbage. We have these printing the waffle. Has ints in here. Yeah, let's make sure this runs, and yeah. Rename word to end, perfect. Yeah, that's basically everything I wanted to do today. That was a lot of stuff. That was a lot of stuff. But we now have reference counting. The background of the compiler kind of exploded into many, many intermediate stages. Yeah, but I think this is nice for future development. Yeah, I guess see you in the next video.